Hey, good morning, everyone. I really wanted first to say huge thanks to the organizers of the MLSS. It's a huge amount of work for a lot of time. 2 weeks is much longer than any other standard academic event. And so really a huge thanks to Makoto and Kenji who are here. It's really a pleasure to be here. I'm extremely happy to be here in Okinawa. I'm sure as many are you. As much as you. And so today I will be presenting a tutorial. So Makoto kindly introduced my work on this area of optimal transport. I will try to provide a survey, a bit of a introduction to the field if you're not familiar with it. And you will see that the first part of the lecture today is going to be about, I would say more like discrete computations. So Makoto was talking about the synchron algorithm and how this was somewhat the workhorse of many recent approaches to optimal transport. So I will first lay out this very clearly. And then in the lecture tomorrow, I will present more neural, I would say continuous formulation of the optimal transport problem. So the outline of the lecture is as follows. We will start now with a bit of a warm-up. I will try to explain optimal transport as an extension of the very simple, I call it CS 101, very basic computer science idea of optimal matchings. And you will see that a lot of optimal transport can be seen as a natural development of this optimal matching problem. And then I will dive into the computations, how this transport problem can be solved and has been generalized in recent years. And then in part 3 and 4 that I plan to push on more for tomorrow, I will basically focus on the continuous formulation of optimal transport. Let me be clear about something. Please interrupt me anytime. I mean, please feel free to just stand up and ask any question if something is not clear in my slides. I will be more than happy to answer questions as they come. So the first question is the following. You enter a room. It's a bit of a puzzle. You see 6 particles that are, in this room, and you cannot distinguish them really. Like they don't. Each of the particles doesn't have like a distinguishing feature, but you see where they are. And as you enter the room, someone turns off the light. So for a few seconds, you have no visibility of what's going on in the room. And then someone turns on the light again, and then you will have seen that those particles have shifted to a different configuration. Okay, so the entire problem of optimal transport can be seen as trying to solve the puzzle, who went where, basically in those few seconds that happened where you didn't have any control and were not able to look at the particles, basically what might have happened that explains that the particles were in some configuration before and now are in a new configuration. So if you now color them, so we're going to distinguish them as like a before and after state, let's say. So red and blue. The question is, how can we explain what happened? And there's all sorts of explanations that can come to mind, and some of them are a bit far-fetched. And in the following, what we'll be mostly focusing on is on explaining that the red particles moved to the blue particles in a way that is, simple. And in that sense, we might think about straight lines. So straight lines, of course, are geodesics for a certain cost. So you can think about geodesics for a certain cost between the red point and the blue point. So how many possible explanations can we find? We have 6 particles on the left and 6 particles on the right. So there are quite a lot of them, as you can probably guess. And in fact, the number of possible explanations, if I'm, again, sticking to those straight lines, is actually easy to figure out. It's just the number of permutations that we can, assign one of the red particles to one of the blue particles. So there are 6 factorial permutations here, so 7 and 120. And so among all of them, we still need to provide, to give an answer and say, okay, I think this is what happened. And the most natural explanation is up to you, to define. You have to define typically maybe a criterion that will help you figure out, out of those 720, this is the one I choose. And maybe one criterion that is quite natural is to start considering a notion of cost. So if nature is efficient, when it's going to move particles from one configuration to another, there is a bit of, energy minimizing principle behind it. And one hopes, that nature is choosing the path, of lowest energy. So what about quantifying energy as just the cost that it takes to move a particle to another configuration? So this we can just simply, call it the cost of going from X to Y for every starting point and every ending point. And then we are going to have, 6 points on the left, 6 points on the right. So here it's 36 possible costs, okay? So we are going to use that information, this cost function between X and Y's. And we are going to come up, and this is the linear assignment problem or the optimal matching problem that I was referring to in the introduction. The natural permutation will be that which achieves the lowest possible, cumulated cost between each of the xi's and the corresponding y sigma I. Okay? So this is, again, the most fundamental problem that you can say in optimal transport, the simplest one. And here you can start seeing that there is a very important ingredient that we have added along the way, which is this notion of cost. Okay? So we will go back to how to define the cost and how impactful it can be. So once you have this permutation, so remember, out of 720, I need to pick one. So that seems doable. The problem is that with n points, 1,000 points, 1,000 factorial, of course, is way too large to enumerate all possible solutions. And so we need to have an efficient algorithm to compute, to minimize this problem. And so the algorithm that people proposed to solve this is called the Hungarian algorithm. Actually, it's Kuhn on the right there that named it after two Hungarian mathematicians that had somewhat, provided the basis for that algorithm. And so Egervary, and Koenig. And so in the 50s, it was fairly well understood, that if you had to solve this assignment problem, there was a practical algorithm to do it. And the algorithm was known to be n power 4 when it was first proposed, and a few years later, a simplification was proposed to make it cubic. So since the 50s, there's been many variants of this algorithm, but roughly, if you want to solve it for any generic cost in any, let's say, dimension, it's going to be cubic. So the other reason you might have heard about this before is because if you take the actual costs that it takes you to go from red to blue and look at the optimal cost, then you have this sum of lengths or sum of costs. And this is known as the Wasserstein distance or optimal transport distance or Kantorovich distance or earth movers distance, et cetera, et cetera. There's many names for it. And this is the distance between the red configuration and the blue configuration. So often in this lecture, we're going to be switching to either of those two objects. One is dematching, the notion you can efficiently move red to blue, and the cost, which is basically the sum of those small, the optimal permutation of the costs. And this is basically the Wasserstein distance. This is the distance. So we have two objects. One is the matching, and the other is the cost of the optimal matching. So if optimal matchings were great, I would probably stop the lecture here and tell you that optimal matchings and the Hungarian algorithm can help you solve a lot of problems in machine learning. But that would be wrong, because optimal matchings are actually useful. They give you the answer that, the very intuitive answer, but they have a lot of drawbacks. So even though people use them in some applications, so a very simple application, for instance, that comes to mind is when you are predicting a set of things and you have a ground truth that is also a set, and you want to be able to find a cost, like a loss function. So this was proposed, for instance, in detection transformers, where the goal is to produce a set of bounding boxes and labels for objects in an image, and the ground truth is a list of bounding boxes and labels as well, and then to find out whether you did well in your prediction, because things should be permutation invariant, you're going to use an optimal matching. But so this type of application works with very few points. Again, the challenge is when n is bigger than a few hundreds. So that's the problem. And then Makoto mentioned something earlier, which I think is really, really important, which is that in applications of all these ideas to deep learning, what matters, as you know, is not so much whether you can compute things easily, but it's more whether you can compute them on GPU and whether they are differentiable. And so let me just show you a little video animation of what happens when you run an optimal matching solver on those configurations. So a bit as what you would expect, you know, because we are dealing with permutations. Of course, here I'm plotting the matchings, the associations, the optimal matching between those blue points and orange points, and I'm slowly, you know, varying the location of the blue points. As you can see, essentially, for a while, the best matching permutation stays the same. So there's not much gradient, if you want, you know, in terms of the solution that we have. And then all of a sudden, it's going to jump to another matching, okay? Which again is normal. We are optimizing over discrete space. The space of permutations is being discrete. When we switch, it's in a discontinuous way. So this is one of the issues that we will try to revisit and solve if we want to use this entire idea of matchings in machine learning. There's a few more problems that one can list. And again, each of those problems is a research opportunity that people have fulfilled, have proposed solutions. So the first one is arguably the matching problem is very intuitive. It's very simple, but it's very rigid in the sense that if we are matching different families of different sizes, then of course we cannot use matchings anymore. We need to somewhat, you know, change them a bit. So if the number of points X and Y differ, then we cannot use, again, this permutation. The thing that might happen also is when we have weighted observations. So if we have, let's say, a probability distributions that is made of atoms with different weights, it doesn't make sense to match an atom that is small to an atom that is large. Another problem that we will also mention later is sometimes in some situations, you might want to match points that are in different spaces. So for instance, a very classic example of matching problem is matching a worker to a task. So imagine you run a company, or let's say you run even a university. You have 100 professors and you have 100 courses to teach. And of course, your goal would be to assign a course to a professor that is not too far from their area of expertise. So either you embed, let's say, your professors and your courses in the same space, and then you do the matching with a cost that is simple, or you directly want to be able to match professors with courses, and in that sense, you don't really have an easy notion of cost between them. So how can you do this matching when the spaces are of different dimension and do not have any simple cost that comes to mind? Another problem that will be even more important is that of generalizing out of sample. So in the very simple machinery of matchings, everything was sample-based, you know, sample on the left, sample on the right, just matchings, and that's it. Could you actually learn from those, you know, starting configurations and ending configurations to somewhat extend, be able to extend or to infer a displacement for a certain point that you had never seen before? So, of course, when we start, you know, switching to this idea of new points that come up, then we can see that what we want to do is go towards a continuous formulation of optimal transport. So in this sense, all of the samples that I had seen before were just random IID samples from the red measure and the blue measure. And I will try to learn in a more classic statistical sense, basically a mapping that will take me from the red observations to the blue observations. So how you want to parameterize this mapping is basically going to make a difference. So by mapping, I mean a function T that is going to learn, you know, from all of the red and the blues and be able to push a new point in the red measure to a blue point in the blue measure. And so this parameterization of the mapping basically, oops, sorry. So this parameterization of this mapping is going to make the difference. And we're going to see that we can parameterize those maps typically as neural networks. And this would be the second part of the lecture. More generally, everything that I've shown you was quite rigid. You know, it was one-to-one, you know, like a function taking a point to another. What if we wanted to have some notion of uncertainty? Rather than assuming that the paths are straight lines, can we parameterize them as stochastic processes, for instance? And we will see that there are links here with diffusion models or the so-called Schrödinger bridge problem. And so when we're going to parameterize our T function, the mapping function, as something that is stochastic, we will move from a deterministic formulation to a more stochastic formulation. So this is a bit, those are the general ideas that are floating around in the area of optimal transport. There are a few more that we'll not have the time to cover at all, you know, during this lecture. But in machine learning, I think those are the main problems. I will maybe spend this little slide on jar. Yes, please.
Hi, thank you. Could you please elaborate a bit on what's the motivation for, like, why is this problem specifically interesting?
Yeah, that's a very good question. So if you think about generative models in general, so there's various answers that come to mind. So in the discrete, I would say problem, when we have, let's say, the red and the blue. Here I just showed you something where I was turning on the light on, turning it off. In practice, what will happen is that the red and blue points are essentially points that come from the same, I would say, original data set, but you only have access to this data set according to two views, and the views are not basically matched. So there are situations where in sciences, for instance, in single-cell genomics, where you can only have access to a measurement once of something because you have to kill, you know, that thing to see what's inside. And so in that sense, you might have, let's say, measurements from one experimental condition. You have measurements of another experimental condition. So we have a lot of points, but you don't have, those points are not matched in a way. So you need to guess, you know, in a way, what could be the best match of a point in the experimental condition with another point. More generally, this idea of, you know, mapping points in a certain distribution and to another distribution is the basis of generative models. So everything that we do, you know, when you use, you know, even starting from GANs, simple GANs, to more elaborate diffusion models, we are mapping something that is sometimes noisy, like Gaussian noise, to something that is structured, has a certain probability distribution, which is distribution of images. And we have to learn that mapping. And we don't know basically the matchings. We don't know that this image, for instance, was matched to this Gaussian realization. So there's lots of, all of the situations where you have two families of things, but you don't know a good matching between them. You have to come up with one. And this will be typically using optimal transport. So the simplest, you know, discrete problem in OT is going to be about, you know, matching points that are in the same space, as I said earlier. So the words that you might have heard about this for this is LAP, so linear assignment problem, Cuturi problem, and then we will discuss about linear programming duality. This is going to be a very powerful tool to help you handle such problems. And here we will be talking mostly about matrices, couplings, plans, and again, this link to Earth move resistance, which was a very big thing in computer vision a few years ago. When we're going to match points across two different spaces, we're going to talk about QAP, or quadratic assignment problem. The other famous keyword is Gromov-Wasserstein, or Gromov-Wasserstein distance, or even fused Gromov-Wasserstein. I will explain basically what this is. And this, I will show, has links to the graph isomorphism problem. So basically trying to compare two graphs, especially when the nodes of those graphs are annotated. When we're going to move to a more continuous formulation, we will have basically this view of, you know, probability densities, and we're looking at samples from those densities. And here we will be talking about functions. So the Monge map is the function that is known to, you know, go from this measure to another. And here I will be talking more specifically, I will be introducing to me what is the cornerstone of this theory, which is this Brognier-Gangbo/Gangbo-McCann theorem, which helps you actually give an analytical formula on what is the best way to transport a probability measurement to another. And I will show that this has links with convexity, and in particular, these results can be used, with neural networks when we're going to look at input convex neural networks, or ICNNs. In the last part of the lecture, I will talk about the dynamic formulation of optimal transport. So this is also known as the Benamou-Brenier formulation. And I will show this as links to the Monjean-Père PDE. And I will also establish some links with flow matching, rectified flows, and in the case of stochastic paths, to this Schrödinger bridge problem. So for this, my part one is done. And I'm going to dive really into computations, I would say, computations of optimal transport and how to solve at scale the discrete problem. So for a while, my main problem will be given two probability distributions, discrete. So here I will be talking about points, xi's with masses ai's, and points yj's with masses yj's. So here again, in this plot, all of the little crosses stand essentially for the locations of the points, and the length of the sticks is the weight. So you have a mass and a point. And I will be placing myself in some space, omega, and then endowed with the cost function c. So my problem will be to transport, again, the mass from the left to the right. So let me give you another historical motivation for this problem that is not so machine learning, but it really explains why this appeared, why this was put on the map in math. And the motivation is, so it's the same setting. We have points and we have quantities of mass, but I'm going to give a more concrete application. Imagine you have mines that are, extracting a resource, and the size of the mine here is more or less proportional to how much resource it extracts. And you have factories which are going to use those resources. And again, the bigger the factory, the more resource the factory needs. And if you have this kind of layout, so you have to transport the resources from mines to factories, then you ask yourself, what could be an efficient way to do this? So actually, 4 mathematicians asked themselves roughly the same question in the 40s. And the reason why this was in the 40s is not a coincidence. This was really a byproduct of World War II. So why is this important in World War II? Because essentially this is when logistics were born. So if you have a country that is in a war economy, or let's say a socialist country that is very centralized, then all of the processes are controlled by a central head of state and also a central organ, let's say. And this is where you can start thinking about doing things optimally. Okay? If this is a free market and everybody does whatever they want, you as a government, you can give incentives, but you cannot direct the resources. If it's a war economy, you are directing everything. And so if you are in a war economy and you are producing, on the one hand, the resource and actually turning it into something else in a factory, you are in the position to basically define an optimization problem and try to solve it. And so this is why all of this science of transport was really designed in the 40s, where people were desperate to actually do things as efficiently as possible. So actually, there is another mathematician called Tolstoy in the 30s in Russia that also started thinking about this in terms of train network, a huge network of trains in Soviet Union, and trying to allocate, move masses optimally. So the problem that we will be faced with, again, is if you are a mine, if you're a mine and you have to distribute the resources, you need to find where you should ship whatever you're producing. And if you're a factory, you need to find out where the resources should come from. And so optimal transport in this case is going to be trying to find the best associations between mines and factories. And how will we actually write this mathematically? Well, it's quite simple. We have, I think, 2, 4, 6, 7 mines and 2, 4, 6 factories. So we will be designing 7 times 6 matrices that will hold coefficients. And each of those coefficients is going to explain how much mass goes from each of the mines to which factory. So we're going to number all of the mines and all of the factories. We are going to Now, keep track of how much is produced in each mine, how much resource is produced in each mine, and how much resources is needed at each factory. And we're going to consider coupling matrices or transport matrices whose sum in terms of rows and sums in terms of columns will lead to basically match those that we've been given. Okay, so any matrix that has rows that the quantities in the rows sum to those red squares and the quantities in the columns sum to the blue squares is going to be a valid assignment. So this is what we will call the transportation polytope. So it's basically matrices of size NM with row sums that are equal to A and column sums that are equal to B. In other words, those are joint discrete joint couplings between two discrete histograms A and B. So this is going to be our optimization variable. And here we're moving away from the permutation, the permutation that we had been discussing earlier on. This is a natural relaxation of permutations. If you remember, permutations can be cast as permutation matrices, and the permutation matrix is a matrix that has ones or zeros. It's a binary matrix with row sums equal to 1 and column sums equal to 1 as well. And so here we have a slightly more general framework. Now, the second thing that is going to play a role, of course, is the notion of cost. Remember, we had 6 and 6, in the first introduction slide, and I talked about 36 possible costs. Here we are going to have 42, 7 times 6. And I'm going to fill this cost matrix, MXY, with the values of how much it takes, to transport from one mine to one factory. So with those two things, on the one hand, a feasible set of couplings, and on the other hand, on the right side, a cost matrix, I am going to define this quantity. I call it WC because somewhat it's a bit like a Wasserstein distance. It's going to be the minimum across all coupling matrices with row sums and column sums A and B. Dot product, MXY, which is my matrix of cost. And here, of course, the dot product between matrices is just simply the sum of Pij times the cost that it takes to go from Xi to Yj. So essentially, this is a linear program, and this is arguably one of the simplest and most fundamental linear programs that have come up in the literature. If you open any optimization textbook, it's very likely that the transport problem will be somewhere in the introduction, trying to explain things to a new audience. And I will try to explain in this slide, a bit with my hands, duality, because this is really the, I think, cornerstone of linear programming and convex optimization. So again, remember here we are going to look for matrices P that have n lines and m columns, and which are such that the row sum is equal to A and column sum is equal to B. And we're going to take the dot product with this cost matrix. And here I have provided an illustration, where I have a configuration of mines, the red squares, and a configuration of factories. This is the blue circles. And when I run my optimization and I get the best optimal matching matrix, what I do get is an association, a bit like when I was showing my permutations. Here, I am going to draw some lines. And the thicker the line is, the more transport between that factory and that mine. Now, let's try to derive duality by hand a bit, if you're not familiar with duality. So the first thing in duality to keep in mind and to always remember is duality is a game where essentially what you're trying to do is flip, whatever was in the objective in the problem and whatever was in the constraints. Anything that was in the objective will necessarily be brought down as the constraints of a new problem, and anything that was in the constraints of the original problem will be brought up, as the objective of the new problem. And the way you do this is typically by introducing a notion of indicator function of the constraint set. So here, my constraint is essentially characterized by the fact, if I remember, if I put aside the non-negativity of the coefficients of P, by those two linear equalities. So I am going to introduce an auxiliary function, which is going to be an indicator function, which tells me whether my matrix P does have the row sums A and the column sums B. So how am I going to do this? Well, I'm going to introduce this optimization problem, which is a bit artificial, which is as follows. I am going to maximize, in terms of alpha and beta, alpha transpose A plus beta transpose B minus the dot product of P with two rank 1 matrices. One is alpha times the vector of ones, and the other is 1 times beta. So let's just look at this problem here in particular. Sorry, this part of the objective. If you look at the dot product between P and alpha 1m, the only thing that you get is basically the bilinear form, basically alpha transpose P times 1s. This is just a linear algebra identity. And 1n P times beta. Okay, again, remember, beta is a vector of size m, P is nm, and then we have a vector on size n on the left. So those are numbers, basically. Okay, so I'm going to replace this, and I'm just going to swap, the orders to make it clear that I have something that looks like something that is easier to read, where I have factorized with respect to alpha and with respect to beta. So why is this clear that this is an indicator function? Well, think about it. I am telling you, just take the difference between, the marginal of P or the row sum and A, and multiply it by alpha. And you can do whatever you want with alpha. And in particular, if you want to make it very large, it will work. So if you think about this quantity here, it should be clear to you that the quantity maximum of alpha beta of those terms is going to be 0 if actually P has the right marginals. Because in that sense, A minus P1 or B minus P transpose 1 are going to be equal to 0. And so if I take the dot product with alpha or beta, it doesn't change anything, okay? But if those two things here, this term is not 0 everywhere, since I can do whatever I want with alpha, remember alpha is not constrained in terms of sign, I can basically make this, as large as I want. For instance, if there was one coordinate where this difference here is negative, I can make that alpha I very, very negative. Or here, if there's a coordinate which is positive, I can make that coordinate arbitrarily large as well. And so this little auxiliary optimization problem is really doing the job that I want. It's basically something that blows up if P doesn't have the right marginals, and it's 0 otherwise. So I'm going to plug basically this indicator function inside my minimization, and now I can drop what I had before. I had constraints that are no longer there because they're handled basically by this. This is a handy tool that blows up if P is not correct, doesn't have the right marginals, and basically stays at 0 otherwise. So I'm going to do a bit of bookkeeping now. I am going to have this big, what looks like a big problem. Okay, the mean of this is the objective plus something that encodes all of the constraints. And I'm going to do a bit of bookkeeping. I'm going to swap things around. I'm going to, in particular, do a min-max swapping. So I don't have the time to explain really why this is valid, but you can trust me, especially in the case of linear programs, this is actually okay. And I am going to do a bit of reordering of terms so that I'm sure that I'm putting all of the terms that are related to P in the right bracket. So after a bit of moving things around, I am dealing now with this max of a mean problem with respect to P with a cost that is something that popped up naturally that includes both this original matrix in the objective of my primal problem, and then something that popped up that depends on those auxiliary variables alpha and beta. And then this is basically a leftover, you remember, of my clever trick to do this indicator function. Now let's look a bit at this term here. This is the minimum for a matrix P that has non-negative entries of the dot product between P and a matrix here that, we just look a bit more closely into what that matrix. But if you think about it, if you just if you're able to take the minimum for any positive matrix of the dot product with P with some matrix, it's very clear that this is going to be either 0 if all of the entries of this matrix are non-negative, because there's not much I can do then in that case. If I want to take as small a dot product as I can between a non-negative matrix and another matrix, if this is all positives, then this will always be non-negative, and the smallest I can do is 0. Or if I am lucky, and it happens that one of the terms in this matrix has a negative entry, just even one, that would be enough. I can, put as much, here mass as I want on that particular entry on the in P, and make this arbitrarily negative. So this will go to minus infinity. In other words, this is an indicator function also of the polytope for alpha and beta, except I have flipped this line here. It's minus infinity here, but it's also useful because if I now replace this term here, this minimum, what I get is basically the max for alpha beta of alpha transpose A plus beta transpose B plus this indicator function. And this indicator function, again, I remind you, the only thing that it is doing is that it is basically keeping track of whether this inequality is true. And when is this inequality true? Well, it's going to be true if alpha I plus beta j is smaller than the cost that it takes to go from xi to ij. So by just doing things manually, we have gone from a primal problem, which is again very intuitive for everyone, I think, because it's very simple. It's really this logistics problem, to a dual problem that is maybe slightly less intuitive, but that is actually the same thing. You can show this. This is very classic linear programming duality. And actually, this is what gave Kantorovich and Koopmans the Nobel Prize in economics in the 70s. And so what is exactly this problem solving? This problem is telling you that for every mine location, alpha, i's, there is going to be a value alpha I for every mine, and there is going to be a value beta j for every factory, such that I will try to maximize the dot product between alpha and A plus beta and B, subject to this alpha I plus beta j constraint. And so if I were to plot the solutions of this dual problem, exactly for the same setting, here is what I would get. I would get color-coded here values for each of the mines and each of the factories. And essentially, a very classic interpretation of duality is a notion of prices. So imagine you are at the top, you are the government, or you are this planning organization that owns both the mines and the factories, and you want to transport optimally the production of the mines to the factories. So this is the problem. Okay, this is a linear program. Maybe you don't know really how to do it. It's complicated. Okay, I'm actually not that interested in actually solving the problem. So I'm going to delegate this task to another company. Okay, I'm going to outsource. And the outsourcing is going to be as follows. I will ask a logistics company, like this could be the Post, to do the job for me. And I will tell them, how much should I pay you, to transport all of those things around? And the company is going to come to me with a pricing scheme, which is as follows. It's going to tell me, okay, I am going to charge you for every unit of mass that I pick up in any of your mines. And I'm going to charge you for every unit of mass that I deliver in any of your factories. And because your factories and your mines are a bit spread out in the map, sometimes it's simpler for me to go and pick up at one mine or to deliver at one factory. So I'm going to give you individual prices for each mine and each factory. So you will have to pay me alpha I dollars, let's say, for every kilo of resource that I pick up in mine I, and you will have to pay me beta j dollars for every kilo that I will deliver at your factory j. So I say, okay, that's good. Then this means that the total amount of, basically what I have to give you to do this service is equal to this, right? Because right now in my configuration, I have AI, kilos of resources in each mine. I have beta j that I need in each factory. So if alpha I is the per unit of mass price, then this is the total, bill that I will have to pay. And okay, we agree on this. Fine. Let's, imagine that I have the Post. Now I have to actually set alpha and beta, right? I don't know exactly what are alpha is and beta j's that will make this profitable. So my goal, of course, is to maximize the bill, right? If I could charge infinite price for those services, then I will make a lot of money. Unless there was an easy way for the conglomerate to check whether my prices are right. And there is actually an easy way for the conglomerate to check whether my prices are right. If I'm starting to give a list of prices, alpha and betas, to the conglomerate as a shipping company, there's a very easy way to check whether my prices are more or less competitive. And it's simply to check that the price that it takes to pick an amount of mass at location I and deliver it at location J will be alpha I plus beta J. And that should be smaller than the cost that is publicly listed to take mass from I to J. So this is the natural constraint that the shipping company needs to observe when it's going to set the prices. So in that sense, the shipping company is just going to say, okay, I'm going to charge you alpha transpose A plus beta transpose B. That's the total price of the transport. And I will find a way to make sure that every time I charge you a unit of mass transported from I to J, it's actually matching the price of the market. And I'm going to maximize my profit. Okay. So that's a bit the story of duality here in one slide. Another very important thing is that duality actually gives you something that is very different and very interesting from the primal problem. Again, keeping on with this analogy, imagine I am the conglomerate and I have sources and targets, and I look at this transport here. If you are thinking ahead for the next step, if I'm able to move the factories, let's say, I'm a big logistics company, maybe I'm able to move the factories, or maybe try to mine some other areas to make sure I pay less transport cost in the future. Well, this somewhat gives you a very clear map of what you might want to do. Here it's very clear that this here mine is very far from everything else, and that this factory here is far from everything else. So if, for instance, I'm able to move the factory locally in terms of gradients, my incentive would be to move this factory, and I know exactly where I should be moving it towards. I should be somewhat following this line. So if I'm thinking about moving locations of discrete probability measures, the primal problem is really where I want to go. So in terms of sensitivity analysis, people would call this sensitivity analysis, if I want to reduce my transport costs, I want to move basically the factory along this line, and this would be probably the best way. And the same thing here for this This factor here, it's serving 3 other mines. So maybe I want to go it somewhere like, the barycenter of those 3 mines. So that applies only to the location sensitivity analysis. Imagine now that I want to, something maybe that's a bit easier, I want to reduce the production in some locations and increase it in some other locations so that I can decrease my transportation cost. If you want to do that, this is really not, this problem is really not giving you this notion of sensitivity. If you want to think about quantities instead, it's the dual problem that is going to give you that answer. Why? Because remember, all of those red and blue values here, alphas and betas, are prices for transporting stuff. So again, maybe I didn't go into the details, but you can have negative prices. It's fine. I mean, as a shipping company, I can perfectly tell you that I'm going to give you $10 to pick up some mass somewhere if I am able to make that difference somewhere else when I'm going to charge you for delivering to another factory. So I can say, I'll give you $10, but you have to pay me $11 when I deliver. It's the same thing as saying that I'm charging, let's say, $0.5 to pick up and $0.5 to deliver. So everything is kind of translation invariant. So prices are translation invariant, and so you can have negative prices. So those prices basically only make sense roughly relative to the other points. So if I look at the prices for only the factories in blue, when it's very clear that the price is lower for those factories that somewhere closer to the center where they're cheap actually to deliver to, and that they started getting higher for factories that are a bit further off. And here, the same thing when I'm talking about mines, when I need to pick up stuff, the heaviest price, the largest price is basically for that factory that is a bit off. So if I want to think about gradients of the transport distance in terms of quantities of production, in terms of A and Bs, basically those are the dual is giving me this. So this is going to come back later in the course when we're going to generalize this. I will not prove it again, but we're going to generalize duality for a continuous formulation of optimal transport. So the primal, again, is in terms of coupling matrices, it's associations between points. The dual problem is prices, vectors of prices, or those vectors of prices are also called potentials. And there is one, I mean, you might think, okay, those are two problems. I just told you repeatedly that they were very much linked, that they are roughly the two variants of the same problem behind. So is there a simple way to go from P star, the best solution of the primal problem, to alpha and beta star solutions of the dual problem? And it turns out that there's a primal dual relationship. It's not completely one-to-one, but there is one thing that helps you basically go from one to the other. And well, sorry, I said it was not one-to-one. It's more or less one-to-one. It's really just a small few details, but it's not an explicit relationship. You have to somewhat leverage this primal dual relationship, also called KKT condition, to understand how you can recover P star from alpha star, beta star. And the relationship is as follows. If the transport matrix is strictly positive in one pair of indices I and J, then it means that, oh, I'm sorry, I forgot the stars here. Alpha star I plus beta star J is equal to CXI YJ. So you have a saturation of constraints that appears. Okay, so this was the general linear programming framework, which in the end we're not going to use a lot, but it's very important to have it clear in mind. Let me just open a small parenthesis to say that the optimal transport problem is actually very easily solved in one dimensions, both in this discrete case and in the continuous case. So imagine your country is a very thin line, actually. So Japan is almost there in terms of rail network. You could have you have a thin rail network that connects the country. You could also think of Chile, for instance, as a very long, thin country. If you have your country, which is more or less a 1D manifold, and you have your mines and factories are located on this 1D line, then transport is trivial. It's basically as simple as trying to transport, whatever mass you have in a mine, you try to transport it to the leftmost factory as long as you can. And when this stops working because you have fulfilled the demand, you move on to the next factory. And if you have sent everything, you move to the next mine. So here is what it would look like. You would just start fulfilling the transport from this leftmost mine to the leftmost factory. And when you stopped, then you move on to the next factory. And so you do this repeatedly like this. So as you can see, sometimes the transport themselves cross, but that's really not a problem because this is guaranteed to be optimal. So whenever you give me two families of points in 1D, values in 1D, I can do optimal transport trivially by just sorting basically those values. So forget about the 1D thing. Let's go to the more general problem. We have this linear program again, and we have to imagine this geometrically. We have a cost matrix, which stores all of the geometric information between the points xi's and yj's. We have a transportation polytope, which is a set of matrices of size nm that have row sum A and column sum B, non-negative values. And we want to shoot basically for the best for the best P star, the best possible matrix in that polytope. So when we do that, what we have to do very intuitively is go as far in the opposite direction as mxy as possible. This is the basis of linear programming. And usually, when you go very far left here in this polytope, you will end up touching a vertex of this polytope. So this is why you will, we usually say this P star is a vertex. And this, I will not go into details, but there are a few linear programming methods to do this. One is the network simplex, and the other is the auction algorithm. And they are all specialized methods, I would say, to handle this kind of problem. The good thing, the glass that is half full, is that this only takes basically n cube log n time if the number of sources and destinations is the same. So I'm saying it's a half full glass because the problem itself is already characterized as n square or nm. So I'm paying a little bit of price to actually solve this problem, which in linear programming is not given. The half-empty glass is, of course, that this is a bit too much, right? It's cubic, so it doesn't scale very well. So that's the first problem. The second problem is in terms of, again, sensitivity analysis and trying to differentiate this. Imagine that I'm going to add a little perturbation on my points X. What I get is this wiggling, of the cost matrix. If the cost matrix wiggles a little bit, then I'm fine. It's still going to stay there in the same solution. But then sometimes something very strange will happen, which is that the cost matrix will be orthogonal to a facet. And although this has probability 0 of happening, what happens a lot is that you're going to jump from one vertex to the other. So whenever you have a linear program or discrete solver, this is, of course, the problem that we have to deal with. And this is what makes this solution P star really not unique always, but most importantly, it doesn't really have a meaningful Jacobian with respect to the inputs. So by Jacobian, I mean that if you vary a little bit the input, you're going to have jumps in what is the solution, the optimal solution. This is what I was representing, remember in the first slide with those points blue that were moving around. Maybe a consequence of this that is not that problematic in general, but still, illustrates the problem is that the quantity itself is not differentiable. Okay, the Wasserstein C of two discrete measures will not be differentiable. So that's a bit of the overview, what we could call the plug-in estimator of the Wasserstein distance, basically running given two probability distributions, xi, x1, xn, y1, ym, try to compute discrete optimal transport between them. And so the first thing is basically how much of a computational cost this will incur. So what I just told you is that if you have two measures of size nm, you have to pay basically this nm log n plus m times n plus m. So that's a bit too much. The other problem that a statistician or a practitioner will ask is basically what is the complexity, statistical complexity of this? In what sense, if you give me samples, what actually does that computation, is that computation stable in terms of samples? Can I expect that if I repeatedly recompute this quantity in terms of samples, somewhat the quantity I'm computing is going to converge towards a quantity in population? So this is the statistical complexity. And it turns out that this is another field, a very active field of research. It turns out this is actually very bad as well. So in short, after presenting you, this linear programming formulation of optimal transport, what I would like to convey is the message that we cannot use directly linear programming to solve optimal transport because it is very unstable in many counts. So the first one is computation is too much. The second is statistically it's not really meaningful. And the third one is basically that we saw that there was no real meaningful differentiable properties of those linear programming solutions. So anything that is going to be applied to data sciences will require some form of regularization. So this is to be the second part of this introduction to the discrete computations of optimal transport. Today, I would say that it would be a bit difficult to use optimal transport directly with those linear programming formulations because, again, computations are slow, statistical complexity is bad, and there is no differentiability. So one very famous, very common workaround to all those problems that I just listed is to regularize the problem. And this is, everything in machine learning is regularization. It's a loss plus some regularization somewhere. And so you might think, why? Well, in this particular instance, again, computational efficiency is going to pop up, statistical regularity, robustness to the cost. So sometimes in applications, this cost function that I've been using around may not be that reliable. So you may not want to put all your eggs in the same basket. Maybe you want to be a bit slightly suboptimal. And differentiability is also going to play a role, and also structure. Typically when we use regularization, either we do this just to make computations a bit easier or more controllable, or also because we have some inductive bias. We want to somewhat promote solutions that have a certain structure. So everything is there in this reg term there. And again, this is always going to be about preferring to go to this P gamma regularized solution rather than spending a lot of computational effort to get to the vertex. So what types of regularizations can we use here? There's many of them, and they have been considered in several works. So for instance, I've listed 2 references here that explore other choices, but there's one that kind of stands out, which is the entropy. So the entropy stands out because you will see that it leads to very simplified computations. So we are going to focus for a little while. I will talk about other forms of regularizations later, but we are going to focus now for a second on entropic regularization. So why entropy? Well, remember that P here is a joint coupling. It's a discrete matrix that has row sums A and column sums B. So in particular, the total mass of P is 1. It's a probability distribution. And so it makes sense to talk about the entropy of P. And if you add this minus entropy regularization to the original linear program, what you get is the convex problem. And you can even say that entropy is one strongly concave function on the simplex. So if you have this minus gamma entropy of P, you get a gamma strongly convex regularization, a gamma strongly convex problem. So we have shifted from linear programming to something that is more common, which is convex programming. So again, here entropy of P is this term. It's a Shannon entropy. And the reason you are going to somewhat derail a bit the linear programming when you add entropies is that you're adding something that is actually going against linear programming. So let me try to explain a bit this in a few words. When you have a linear program with n variables and p constraints, the solution of a linear program will always be a vector that is very sparse and only has p values that are non-zero. So in our case, when we are running a linear program, I'm just going back for a few slides here. Here, if you remember, here I had 4 factories and 6 mines. So my matrix of transport is in principle 4 times 6, 24. And it turns out that in the solution here, I've just printed 1, 2, 3, 4, 5, 6, maybe 7 lines. I'm not sure because they're in the middle. So out of 24 possible connections between 6 mines and 4 factories, there's only 6 or 7 that are basically activated. And this is not a coincidence. When we are going to compute a linear program, by definition, if we have nm variables and n plus m constraints, the optimal matching matrix or optimal coupling here will have can only have up to n plus m non-zero values. Okay, or let me rephrase this a bit more rigorously. There is always going to be a solution that has up to n plus m non-zero values. All the rest is zeros. So if we are going to transport, let's say, a histogram of size 100 to another histogram of size 100, which is what I'm illustrating here. So again, this is just 1D distribution. This is a histogram of size 100 on the left and a histogram of size 100 on the top. Then the optimal transport matrix, 100 times 100 matrix, only has up to 200 non-zero values. So it's very sparse. Okay? And a sparse probability distribution, that is a probability distribution that has a lot of zeros, is highly non-entropic. Okay? It has very, very low entropy. And so by adding this regularization minus gamma entropy, what I'm basically going for is something that is against the common knowledge of linear programming. I want to have a solution that has smaller sparsity. I want something that is a lot of non-zero values. And the higher my gamma regularization will be, essentially, the more entropic the solution will be, and the more blurry it will become. So I want to insist that the original linear program promotes solutions that are very sparse. The second you add some entropy regularization, you're asking for non-sparsity, okay? And as you go in this regularization path where you increase the value of gamma, in the end, what I am going to ask for is something that is maximally entropic. And maximal entropy in the case of coupling matrices is just the product of the two marginals. So in the end, the only thing that I will get is just the product of this distribution times this distribution. So the reason why entropy is actually very practical is that it leads to a very simple algorithm to compute the solution. And this simple algorithm is due to the fact that the solution itself of this entropic regularized transport has a very nice factorization. So if you just apply what is known as the Lagrange method of multipliers, what you can very easily show is that the solution of this regularized, a linear program will have a certain form, which is as follows. The best solution P gamma is equal to a diagonal matrix times the matrix K times another diagonal matrix. And diagonal matrix here is basically generated by a vector U that is non-negative, a vector V that is non-negative of size n and m respectively. And K here is given. It's just basically exponential, element-wise exponential of minus the cost divided by gamma. So the way you can prove this, I left this on the slide to basically illustrate it. It's very simple. You just introduce dual variables. Remember, the alphas and betas should sound familiar. They are the same alpha and betas actually that we had when we were talking about duality. And by just using a simple this identity that the derivative of the Lagrangian should be equal to 0 for every entry of the primal solution, we get that the primal solution has a very explicit factorization. It is basically equal. There must be prices alpha I and beta j's such that the solution Pij is equal to exponential alpha I divided by gamma, exponential minus Mij divided by gamma, exponential beta j divided by gamma. And if I call Ui and Vj those exponentials, I get my solution. So here I'm just showing two things. That basically the solution has this specific factorization. And maybe another side comment is that it seems, and I will show it a bit later, that there is a direct relationship this time between the solution and the prices. Now remember, I told you that for linear programming, what you had is a primal dual relationship that was going through these KKT conditions. Here, actually, there is an explicit relationship between Pij and the prices alpha and beta j. So how do we get to this? The first thing is, what does it look like to regularize again with entropy? When I'm going to contrast the solution that we had, you remember when we were doing the permutation problem between those triangles, the blue dots and the crosses, and I'm going to show you how the solution changes as gamma increases. So when gamma is equal to 0, which is the case here at the top, here it's written there, this is the optimal assignment, visualized on the plane. And here I'm showing you P gamma, or basically the optimal transport matrix. Here I didn't, I'm not so careful. I didn't number out each of the elements, so you will not be able to see a correspondence between left and right. But at least visually, you can see that, with gamma is equal to 0, of course, I have something that looks like a permutation matrix, a binary matrix with a lot of zeros and very, very sparse. When I'm going to add, a bit of gamma, you should be able to spot a few bluish lines that start, showing some association that starts to increase between points. And as gamma increases, you will see, of course, on the right-hand side, my permutation matrix is getting a bit more populated with values. So before I had something that was very clear-cut, 1, 0. Now I'm starting to see some intermediate values. And what you see is that essentially the transport is getting blurrier and blurrier. And so for very large gamma, as gamma increases, let's say there, here at this point, gamma is so large that the transportation matrix is uniform. And here it's actually equal to 1 divided by n squared. It's the product of the two marginals because here the marginals are uniform. I only have, I think, 20 points. So it's basically, the values here is basically it's represented as the blue, but it's all of them are more or less equal to 1 divided by 400, 1 divided by 20 squared. So this is the roughly what you should expect, when you start increasing gamma. I forgot to mention that there are links, in the PDFs to a collab. So every time you have a collab link like this one, you can actually rerun the computations that created those figures. So this is a bit of a computational comparison of various implementations of this synchron algorithm. Here I've compared two famous Python toolboxes, one that I maintain actively called OT, and the other is POT, Python Optimal Transport. And this is just to tell you that essentially the scaling of the synchron algorithm is quadratic in the number of points. So here I just show you basically what was happening with gamma as gamma was increasing. I haven't gone into the details of how to solve this problem. So the one thing that we know is that the solution has this specific factorization. Again, it's a vector diagonal times k times a vector in diagonal form. So let's try to derive this synchron algorithm, from first-hand principles. I know that this is the solution that I'm looking for, this P gamma. I know that the solution has the right marginals A and B, okay? So let's try to leverage those two things together. I know that the solution, times ones should be equal to A. The solution transpose times ones should be equal to B. Okay, those are the two things that I can rely on. I'm going to simplify a few computations. So diagonal matrix times ones is, of course, the vector itself. Then diagonal matrix times a vector is just the element-wise product of two vectors. And so I'm just going to simplify those two things. And I have that there is one iteration that needs to be done. Sorry, the two vectors u and v satisfy a set of nonlinear equations here. U is equal to A divided by KV, and V is equal to B divided by K transpose U. And so what I'm going to do, if I need to find U and V that satisfy these two equations, is just repeat this iteration. Repeat the fixed point, basically, that takes U and V and transform them to new U and Vs. And the iterations are as follows. Again, you start with a V that is arbitrary, typically a vector of ones, and you set U to be equal to A divided by KV, and you set V to be equal to B divided by K transpose U. So this is a synchron. This algorithm was proposed by Synchron in the 60s. If you look a bit more closely into the story of this algorithm, you find it, mentioned earlier on without any proof in the 40s. The idea of adding regularization to a transport problem was already proposed as early as the 60s. And what Synchron did was basically provide a proof of convergence for this algorithm. So again, this idea of adding entropy to a transport problem is something that economists, found first. So economists actually defined first the optimal transport problem because this was related to a logistics problem. But economists also found out quite early on that the solutions of optimal transport, like those very sparse matrices, were not very useful in practice. They were trying to compare actual transportation patterns that they would measure in nature and the solutions of optimal transport. And they were saying, okay, one is very sparse, but we never see something that sparse in nature. So we want something a bit fuzzier in our model. And they added entropy and they called it the gravity model. So you can see this, for instance, in this Wilson or in this Erlander paper. And this idea of matchings with a bit of blur was used repeatedly in economy. So people like Galichon, for instance, also reintroduced it in 2010. And my contribution in this area was to rediscover, as everyone else, this algorithm, but insist on the fact that it was parallelizable on GPU. So you can actually get a routine that solved transport in a certain way that would fit better, accelerators, and also the differentiability aspects. The differentiability being very important for any subsequent, computation. So if you have been a bit puzzled by this synchron algorithm and you come from more like a hardcore convex optimization background, you can forget about synchron in a way. My explanation about balancing out matrices and etc. And you can actually rely on something that is maybe a bit simpler, which is just simply block coordinate to set. So why is that? Well, if you think about this regularized optimal transport problem, this was the primal problem. I just regularized it by adding this gamma entropy. Well, it must have a dual formulation. And I'm going to call this the regularized dual formulation of optimal transport. And you remember that in the original dual formulation, I insisted quite a lot on this. My two vectors of prices, my alpha i's and beta j's, had a constraint that alpha I plus beta j was smaller than the cost between xi to ij. Well, it turns out that when you compute the dual of this primal, you actually get rid of this constraint, and it appears in a regularized form. So in the original dual formulation, remember this was max of alpha transpose A plus beta transpose B, and there was this alpha I plus beta j there that were alpha I plus beta j smaller than the cost between xi to ij. That was a bit annoying. Well, that thing is gone now, and it's a double sum, which is basically the sum of exponential. I'm sorry, this maybe a d power p should be a cost. I've been using d power p and cost interchangeably in some of the slides. Exponential minus the cost between x, I, y, j divided by gamma plus alpha I plus beta j divided by gamma. So it's basically this bilinear form. So once you realize that the dual of this regularized problem is this, there is a very simple approach to solve this problem, which is basically gradient ascent. Why? Because this is a unconstrained, like the primal problem, even its regularized primal problem. Now we have an unconstrained optimization problem. So we know that unconstrained can be solved using simply gradient ascent, because here also this function here is concave in alpha and beta. And one thing you can do when you have two variables in a concave problem or convex problem is do what people call block coordinate ascent. So you just focus on one variable, increase the objective as much as you can, and then focus on the second variable and increase as much as you can. And here it turns out that actually there is a closed form update for those gradient updates. The closed form update is basically saying that if you change alpha to this thing, then you cancel out the gradient of this energy. And if you change beta to this thing, you cancel out the gradient of this other energy. So in other words, we can solve, we can see synchron as simply a dual problem. Now let me try to link this idea of synchron divergence or synchron type of computation of optimal transport with the original linear program formulation and what people call MMD or maximum mean discrepancy. So the idea is that essentially there are three notable points now, to compute, to look at in the polytope of transportation matrices. We can start with P star, which is the optimal transport, this very sparse matrix. When we increase regularization to infinity, what we get is essentially a transport which is just the product of the marginals. And this is what I call AB transpose. And then we can interpolate between the two with a varying regularization gamma. And here we will get this P gamma, okay? Well, it turns out that if you look at the transportation cost for each of those three matrices, you will have, of course, something that will be bounded. One is going to be bigger than the other, which will be bigger than the other. But what you can also do is use those quantities and maybe polarize them in a careful way to define essentially three divergences or distance functions between probability distributions. And again, this is going to be the energy distance or maximum mean discrepancy. Then this polarized W bar here, gamma, is the essentially equivalent of the MMD for the regularized optimal transport formulation. And then W is, or WP here is my classic Wasserstein distance between the samples X and Y. So those things basically interpolate one with the other. And so there is a bit of an analysis that has been done on those three quantities between MMD, or again, energy distance, those are the same thing, and the Wasserstein distance. So the MMD is very simple to compute in the sense that its complexity is at most quadratic in the number of points. Because it's very simple to compute and fairly simple even to interpret, it has good statistical properties in the sense that, you know, the estimator, when the number of points is n, converges as 1 over square root of n. If you look at the Wasserstein distance, it's the complete other end of the spectrum. It's something that is very hard to compute, and it's also very unstable because it has this statistical complexity of 1 divided by n power 1 over d. So again, this statistical complexity only makes sense if you specialize it to a certain cost in a certain, you know, setting. So if you are comparing it, you know, comparing point in RD with the squared Euclidean cost, this is the type of sample complexity you will get. And essentially using entropic regularization is somewhere in the middle. It is not the cubic complexity of Wasserstein. It's not the simple quadratic complexity of MMD, but it's somewhere in the middle. And it's not this 1 over, I mean, the curse of dimensionality that we have in Wasserstein at the bottom, nor the very simple parametric rate that we have at the top with MMD. It's somewhere, again, in the middle. So with this, I'm going to close a bit the parenthesis on synchron and entropic regularization, and I will show you other tools that people have increasingly relied on, you know, in the literature to kind of boost a bit the performance of those solvers. So the first thing that people have been using recently is the notion of unbalanced transport. So what is unbalanced transport? It's the idea that sometimes when you're actually dealing with data, you might want to get rid of some of the points. Some of the points, you can interpret them as outliers, and you would like your algorithm to be able to actually do this elegantly. So one of the ideas that was proposed in around 2015 and 16 is this idea of somewhat dualizing the constraints that, you know, the matrix P should have row sum A and column sum P. So how can we dualize, you know, such a constraint? Well, essentially, we're going to penalize. We are going to still look for our matrix P that has a dot product with MXY, but we are going to ask that a certain divergence between the row sum of P is not too far and A is not too large, and a certain divergence between the column sum of P is not too large from B. So this divergence might be pretty much whatever you want, but the computations are a bit simpler where it's the Kullback-Leibler divergence. So here, again, this is the Kullback-Leibler divergence between non-negative vectors of size n and m. So this is not the standard Kullback-Leibler between probability distributions, because here, this P1m may not be a probability distribution. And it turns out that if you use this penalized formulation and you still keep the entropy of P, you know, that we introduced earlier, you still get a very simple algorithm, a synchron-esque, you know, type of algorithm. So again, if you want to solve this optimization of P that doesn't have, you know, marginals are too far from A and B, and you still use entropy, then you just need to run a synchron algorithm, which will do the same updates, except that element-wise, there's going to be a small correction in terms of the exponents. So that's going to be very simple to implement. So let me just try to show a bit what happens when you do that. So one thing that you can notice is that something that pops up quite naturally is two coefficients that we call tau A and tau B, which are basically those ratios here. And those why is it natural? Well, because those ratios are between 0 and 1. So in a way, if row A becomes infinite, then this ratio goes to 1, and you recover the original synchron algorithm. If tau A and tau B are equal to 1, essentially it means that those two divergences have an infinite weight, and so we go back to a constraint problem. So this is again my original problem. So I'm going to consider one case to start where row B, my penalization is infinite. So what does it mean that my penalization here is infinite? It just simply means that I want the column sum of P to be equal to B. I enforce this if you have infinite penalization. So this means that the column sum of P is constrained to be equal to B, and I'm going to let the row sum of P roam free. So again, think about my original problem. You know, I was running optimal transport between those blue dots and orange triangles, and I'm starting from the position where row A is equal to infinite, which means that this tau A here is equal to 1. So this is the transport. Again, I already showed you this earlier on. And now I'm going to essentially decrease tau A so that it becomes smaller and smaller. And what you can see is that as I am decreasing tau A, some of the points that are far from everyone else starts actually getting less and less mass transported. So essentially, as my tau A goes to something that is small, I start seeing the following phenomenon. Some of the blue points are associated to two crosses, and some of the blue points are associated to no one. And if I go a bit deeper, what I observe is essentially that when tau A goes to 0, all of the orange crosses are basically matched to the closest blue point. Because this is naturally what happens when you do matching without a mass constraint on the target or on the source here. Essentially, if you're free to not follow the marginal, you are only going to match every point to its closest point. So in a way, the nearest neighbor assignment can be seen as some degenerate form of transport, where you are going to match all of the points in some measure to some other points in target measure. And you don't really care about whether some of the points in the target measure are covered or not, or some of them are overloaded. So again, this is what happens. And in the end, of course, you just see this kind of closest, nearest neighbor matching problem. Now, imagine that I'm going to actually keep rho A and rho B, both of them to a certain value. So neither is going to infinity. And I'm going to set them to be equal to the same value. So in a way, rho A is equal to rho B. Okay, so tau A is equal to tau B. Again, this is balanced. And I'm going to decrease. What you end up seeing is a transport matrix P that can basically transport whatever it wants without regard to conserving the mass. And so if tau A and tau B go to 0, essentially the only thing that you will keep on seeing in the transportation matrix is the closest neighbors that only pop up. So this is roughly the idea of unbalanced transport. Of course, needless to say that it's a bit tricky to set those rho A and rho B right, because this is yet another parameter to handle. But what people have shown is that in a lot of applications with real data, actually this makes a huge difference to get rid of outliers. So it's neither the regime where rho B and rho A are infinite that works. It's not the regime where rho A and rho B are 0 that works, or either is 0. It's basically the regime where you are promoting some form of transport that is balanced, but not completely balanced. I am going to make a very brief reference to differentiating the optimal transport cost. So by differentiating transport cost, again, I would like to go back to this original motivation of thinking what happens when I am going to introduce a perturbation on the weights. I change a bit the weights. What is the gradient with respect to the weights of my Wasserstein distance? And what happens when I perturb the locations? If I change the points, what happens? So it turns out that if you look at the distance itself between those two configurations, or basically the minimum value of the optimal transport problem, they can both be handled using what people call the Danskin theorem or the envelope theorem. So essentially, if you are going to look at perturbations of locations, you just look at the primal problem and freeze the solution. If you look at the perturbations in terms of weights, you look at the dual problem and freeze the solution and pretend that nothing has changed and differentiate that quantity. So let me, for those of you who might not remember the Danskin theorem, here is what the Danskin theorem says. It says, if I have a problem, function f of x, which is defined implicitly as the minimum of a certain function g of x and z, okay, there's an auxiliary variable z and I'm minimizing over z. And I am calling these minimizer of this g of x, z star of x, so it's the argmin. Then what the Danskin theorem tells you is that the gradient of my function f of x here is equal to the gradient with respect to the first variable of g of x computing at z star x, z star x. So why is that a result? Well, it's a result because if you think about what the chain rule would tell you, the gradient of a function f of x, if x here appears twice, in g of x, z star of x, then if I had to compute the gradient of this function, I have to compute the gradient, coming out from the two arguments. So x is appearing here and x is appearing there. okay? So if I want to compute the gradient in that case, I should first state that there is going to be gradient that comes from x in the first variable and in the second variable. And in the second variable, you see that there is basically an application, which is basically that which to x associates z star of x. And so I need to differentiate that again. And so the actual formula for dansking here, for the chain rule, would be that if f is defined implicitly in this way, then the gradient of f of x is equal to this thing plus this big chunk here that tells me how does z star vary as a function of x. So this is the Jacobian of z star as a function of x, times the gradient with respect to the second variable of this thing here. Well, the reason we can get rid of this term here is because by definition, z star of x is the minimizer of this problem, therefore its gradient is equal to 0. So this is what will make our life simpler to differentiate quantities that are related to optimal transport. I will stop here and continue this tomorrow morning with you. Thank you very much.
Okay, good morning. Then let's start today's first lecture by Professor Marco Cuturi. Okay, then let's welcome again.
Thank you. And good morning, everyone. So as I was looking at my slides yesterday evening, I realized we're a bit late. So I will have to skip a few parts in order to prioritize some more important areas. So I will skip in particular than what's coming in the next slides. I will just skip those slides. But just to give you an idea, the slides are about what happens when you want to differentiate the Wasserstein distance between two probability distributions. And as I was explaining, it's basically whether you want to have an idea, a rough idea, or the gradient of what's going to happen if you change the weights of one measure, or if you change the locations of one measure. And in both cases, what I wanted to say in the when I was closing the presentation, is that when you are differentiating the value of a minimum, so again, if you take a step back, the Wasserstein distance is something where you give inputs, some data, and you get a minimization problem, and you output something, a real number. When you want to differentiate that, usually you can use what's called the Dansking theorem or the envelope theorem to differentiate it painlessly. So it's not too complicated. Yesterday, I showed you this small proof where if you have a function that is defined implicitly, you can then take advantage of some identity in terms of one gradient here to cancel out terms and just differentiate the function here. So here our function is g of x and z star of x. So it is defined implicitly somewhat with respect to z star of x as a function of x. But you can forget that z star was a function of x when you differentiate. This is the Dansking theorem. So this means that if I want to look at this cartoon and I want to change a little bit the x, here my p star hasn't changed, but what has changed in the quantity that I'm looking at is basically the other part of the objective, basically. It's as if, we were thinking that with a small variation of x, the optimal transport is not going to change. The only thing that is going to change infinitesimally at the first order is the cost matrix. And so the only thing we need to differentiate against is the cost matrix. That's a bit the idea of the Dansking theorem in this case. So differentiating the Wasserstein distance is easy. What is going to be much harder, or something that we might need more heavy mathematics to handle, is when we want to differentiate the solution. So rather than differentiating a minimum value, differentiating an argument. And so by differentiating, I mean trying to predict how p star is going to change with respect to changes in x in this case. And here you can see that this is very badly posed for the linear programming formulation, because essentially here p star didn't change at all. And if I continue my perturbation, remember, p star all of a sudden is going to jump. So this means that, in other words, the differential, the Jacobian, how p star changes with respect to some inputs is very hectic. It's either flat or big jump. And if you want to use this p star assignment in some part of your deep learning pipeline, then you're going to be screwed, right? It's going to be a big problem. So here the solution is again to use regularization, because in a way, you can see intuitively that if you regularize your P star and turn it into a big P gamma, this is like this convex, strictly convex optimization problem. So you have uniqueness of the solution. Then you can have this mental map that the P gamma is going to vary continuously with respect to the inputs. And you can see this, for instance, in this plot. Here I'm going to do the same game of looking what the optimal assignment permutation looks like when I'm going to vary my blue points. And I'm going to plot you, on the other hand, on the right side, the same solution that is found by Synchron. So if you look at this, you see that Synchron is doing this great job of distributing a bit of the mass all the time so that things keep being continuously differentiable, whereas the hard assignment on the left jumps from one assignment to the other. And so this idea of trying to predict what is going to be the changes of the optimal transport matrix with respect to the inputs, this Jacobian, or more importantly, if you're doing deep learning, usually whenever you have a Jacobian, you should think about using the Jacobian transpose, because this is the basis of backpropagation or reverse mode differentiation. We want to be able to somewhat compute that, apply this transpose operation on any matrix. And so this was explored in a few papers. In OtJax, our toolbox, we have implemented this natively, so you can actually differentiate automatically, this P gamma with respect to the inputs. And this is where I'm going to be a bit brief. There's essentially two canonical ways to handle the differentiation of an argmin. So if you want to differentiate the output of an optimization problem, you can either use what people call unrolling, which is essentially looking at the algorithm that got you that output, this matrix, and think of this as a big neural network that has some kind of deterministic, parameters, and just unroll it. So it's as if, it's more like a programmer view when you're going to be given, let's say, 100 iterations of your fixed point algorithm. You stack them together. It's like a stacking of basic operations in a neural network, and you just backpropagate. And the advantage of this is that it's simple. There's actually conceptually, it's very simple. The drawback is, of course, that you need to store all of the intermediate outputs of your Synchron algorithm in this case. And also, the other drawback is maybe because you're going to usually stop a bit early your fixed point, you might not get actually to something that is the true solution. So this is usually not the biggest problem. The biggest problem is more like the memory problem. So that's the first programmer view. The second one is a lot more involved mathematically. It's using the implicit function theorem. And it's essentially taking advantage of what you know about the solution. The solution is basically satisfying some root equation. In this case, the root equation is going to be the fact that the solution to your problem, the Synchron dual problem, is going to satisfy some gradient that is equal to 0. And you use that to actually define a root function that you're going to differentiate using the implicit function theorem. So I'm going to skip a bit this because if I wanted to take the time to go a bit into this, it would take a few minutes. So essentially, it's going to be about using several tools from automatic differentiation, and they're all very well implemented in JAX. So let me just skip a bit, but just to tell you in 10 seconds, this is implemented in our toolbox, so you don't even need to know about this. You can actually differentiate or call differentials of the outputs of the Synchron algorithm using OtJax. So I'm going to also be very brief on the remaining parts about the discrete computations. Just to mention that aside from the Synchron algorithm, there have been a few proposals, to have like faster solvers for the optimal transport problem, the linear optimal problem, and also the quadratic that I'm going to introduce. And if you take a step back, what we did with entropy, we said, okay, linear program is going to output something that is very sparse. I will go for something that is a bit blurry, and this maybe is actually better because I have faster computations. If you think about the linear programming solution, it's also going to be full rank. Taking again a step back, remember the optimal transport problem is this generalization of the optimal permutation problem or the optimal matching problem, and the matching matrix or permutation matrix is full rank, of course. It's just a scramble identity matrix. So what we're going to say is actually, if I can leverage this, can you give me a transport matrix that is low rank? I know it's not going to be anything like the true optimal transport, but maybe because it's low rank, computations are going to be faster. And this is actually what we found out. So if you think about a coupling matrix of size nm, with a synchron algorithm, the complexity is typically quadratic, so it's of size nm. So this can be very large when n and m are hundreds of thousands of points, and so not very tractable in those very large scale problems. So what we thought is, okay, let's focus on low rank coupling matrices. So maybe some of you here know about this very central theme in linear algebra, which is to look at a matrix and try to have a low rank approximation of that matrix. And usually this can be called, this is the SVD, of course, singular value decomposition, or non-negative matrix factorization when the entries are non-negative. Here in our case, it's a bit more complicated because not only is our matrix or the matrix of couplings that we're looking at, they're non-negative, but are also probability couplings. So this means that we need to take into account those two constraints to come up with a reasonable approximation that is low rank. And what you can actually show is that if you have a matrix P that has row sum A and column sum B, that's a coupling. But if you have a matrix that is of row sum A and a small vector G, that's another element in the simplex, and a matrix R that is row sum B and column sum G, so they share the same column sums, then you have that this matrix here is also a coupling of row sum A and column sum B. So this is like a nice factorization. Notice that there is a diagonal of 1 over G here to kind of normalize things. And this is actually known in statistics. It's the non-negative rank of a probability distribution. And if you can show that a coupling is factorized exactly with this formula, with this shape with a small r, then people say that basically the number of latent coupling can be factorized with latent variables, with r latent variables. So this was used in statistics before. But for the purpose of our computations, what we're only going to do is say, okay, actually, we were trying to look for P matrices that were good, cheap couplings with respect to transport. Now let's just focus on something that is a product of Q, a diagonal of 1 over G, and R, and see what happens. So of course, now we have 3 variables. We have loss convexity. That's the biggest loss in this scheme. But what we get in exchange is every time we are going to do alternate optimization on each of those factors, we end up optimizing a smaller optimal transport problem. Here, the problem is of size n times R. Here it's m times r, and here it's r. It's not even a problem. It's actually a closed form update. And what we do gain is, imagine n and m are hundreds of thousands of points, and r is 100. Well, it's significative, right? We've gone from quadratic to linear. Except for one part, which currently, if I show this here, is still quadratic, which is the computation or the recomputation at each iteration of our algorithm of a cost matrix that is going to be of quadratic or even cubic cost. It's going to be NMR. So what we use here, we say we're going to use entropy here to make those small optimal transport problems more amenable using synchron. Plus, we are going to leverage, maybe for the first time, the fact that the cost matrix here is or can be low rank. And this is always true, for instance, if you use a squared Euclidean distance, as we all like to use in machine learning. So if you're using optimal transport between hundreds of thousands of points that live in some space of dimension D, you can show that your squared Euclidean distance matrix is itself low rank. And so we can leverage this to say that, for instance, this is going to be of size n times d, d times m. So this is basically a low rank dimension. So again, if your points are in dimension d, you can show that any squared Euclidean distance matrix is going to be of rank d plus 2. So that's the good thing if you use such costs. And so this becomes now linear. So overall, we have an entirely linear pipeline, linear time pipeline to solve optimal transport, except, of course, this is not convex, so we need to be a bit mindful about initializations. Just a small illustration, when there is not a rank, so R equals -1 means it's just the original optimal coupling. when we do have a rank that is quite high, we can see that essentially this method tries to find a few bottlenecks to transport from one mass to the other. And so when we are going to start decreasing the rank, it's going to become more and more uniform up to the point where much like the entropic regularization, when entropic regularization goes to infinity, we recover the product of marginals. When the rank goes to 1, we also get the coupling that is the product of marginals. So essentially, it's kind of two completely orthogonal views on the same problem of trying to find quickly optimal couplings. The first one is this rank thing. So the higher the rank, the closer to the original solution. The lower epsilon, also the closer to the original solution. And when you let epsilon go to basically a larger value or the rank becomes small, you go towards this product of marginals type of coupling. So I'm sorry, I'm going a bit fast, but this is basically the idea. And the main benefit of this method, the low rank method, is that we can now reach computations that are of the order of hundreds of thousands of points. And you can also see somewhat that what these computations are doing when they're comparing two distributions is that they're trying to do some kind of k-means of the intermediate measure between the 2-point clouds that you're transporting. So a cheap way to do transport would be to cluster the first measure and the cluster the second measure and then transport the cluster centroids. This would be like a two-step procedure. What this method is doing is simultaneously trying to do some kind of clustering between the two measures that it's transporting. So now let me briefly talk about the Gromov-Wasserstein problem, which is this quadratic assignment problem. It is increasingly important in the literature, so I think it's useful to know about it. The problem, if you remember my introduction slide yesterday, was I have some cases where I might still want to match 2-point clouds that live in completely different spaces. So this could be as easy as, if I have a 3D scan of a person and I have a picture of another person in 2D, can I draw some kind of correspondence between some areas in the 2D picture and areas in the 3D scan? And any one of us here would do this very easily. We are able to do this correspondence, but can we actually find an algorithm to do this? Also, another aspect that sometimes people use is, if I look at my two hands, if I do optimal transport between the fingertips of my two hands, if I just use the original formulation of optimal transport, actually my thumb is not going to be mapped to my thumb if I rotate or move my right hand like this. So optimal transport is not invariant to basically rotations, even when the 2-point clouds are in the same space. So maybe what we'd like to find is a notion of correspondence or matching that is going to be invariant to such transformations. And I know that my thumb, right thumb, and my left thumb should be aligned wherever I'm moving my right hand. So we're going to get both of those two things with this tool of the Gromov-Wasserstein alignment. So the alignment is as follows. What it will try to do is, rather than find a notion of I want this point to be matched with that point with a certain cost, what it will try to do is promote alignments that are isometric. So let me explain what I mean by this. By isometric, I mean that if, for instance, my alignment is matching x1 here to y3, and I am proposing an alignment that is also matching x2 to y1, so I'm simultaneously looking at two entries in my permutation matrix or transport matrix, then I will want some conservation of distances. Because although it's difficult to compare the left points with the right points, it's usually easy to compare the left points within themselves, like to have like an intra-distance, and compare the right points within themselves, again, another intra-distance on the right-hand side. So my goal would be to say, oh, actually, you know what? If you're proposing this, x1 goes to y3 and x2 goes to y1, I would like to check that the difference between the cost between x1 and x2 is not too far from the difference from the cost between y1 and y3. Okay, so this is what is represented in this objective here up on the left. And as you can see, this is very intuitive, but it's a bit nasty computationally, because now this is a quadratic function of a matrix that is itself of size nm. So at least on paper, it would be like a Kartic, complexity in terms of, looking at all of the pairs I prime, G prime. Now, in practice, what you can show if you use this particular cost, there are other costs that have been proposed, but this one is nice because if you look at the above, basically what we have is a quadratic function of P. That's fairly clear. If you look at the gradient of this quadratic function, you will have a linear function of P. That's also quite expected. But this linear function of P is actually quite easy to compute, well, relatively easy, because it's essentially proportional up to some constant terms, if P has the right marginals, that is equal to this product of three matrices. It's the cost 1 times P times cost 2. And so at least if you're only doing some kind of Frank-Wolf type algorithm, where rather than trying to minimize this energy directly, you linearize it iteratively, and then you again call a linear solver again and again and again, then the only thing you really need to compute is basically this gradient, and that's just product of three matrices here. And so here you can use any linear solver of your choice to do this inner iteration. And this could be entropy, this could be rank P. And again, this is implemented in OptimalTransport, and so you can have a look at our small tutorial on Gromov-Wasserstein. Let me say, maybe, no, I will skip this, but believe me, when you use the low rank solver, things actually still work. So we recently proposed for the first time a linear time solver for Gromov-Wasserstein. And this is something that is quite handy for some tasks in biology, because when people want to align cells in multiple spaces, like multi-omics, people call this multi-omics, and have hundreds of thousands of points, actually this can work. But I will just keep a bit. And also there is a generalization called the fused Gromov-Wasserstein problem, where we are trying to fuse both the quadratic part and also maybe some linear term, or basically classic transport term, where you have a cost matrix that is coming from a common, let's say, representation of some of the data. And this is related to the graph isomorphism problem. Essentially, the setting is that of attributed graphs, where a node has a feature representation. So even though maybe the left and right point cloud live in different spaces, maybe a different graph, you are still able to compare nodes one by one, thanks to some feature representations. And so you can actually merge those two viewpoints in this fused Gromov-Wasserstein setting. And again, this is also handled with a low rank formulation. And this was the basis of a toolbox called MOSCOT, multi-omics single cell optimal transport, that uses OptimalTransport in the background. So there's lots of demos of this. So to summarize in a few words, there's an entire zoo now of linear or of optimal transport solvers. Here in this y-axis, what I represented is basically the classic problems that we're faced with. We started with a linear optimal transport problem, then we went with a fused Gromov-Wasserstein problem. So this is more complicated with quadratic terms. Then we've also mentioned this unbalanced alternative of trying to penalize for a difference in marginals. There is also, as you can expect, an unbalanced fused Gromov-Wasserstein generalization. In the columns here, I'm basically outlining three main families of solvers: the linear programming formulation using the network simplex, entropic regularization, which we've been going quite into, and then the last one, the low rank, which I just presented this morning. And it's just to say that all of these areas of the matrices are being filled now with solvers, and so those are tools that you can readily use, with your data. Let me just skip this. So here I put in the slides some, perspective, some further reading if you are interested in this. There's many areas to explore, in each of those problems, has been carefully investigated, whether there's opportunities for speed up, whether, we can say interesting things about statistics, et cetera, et cetera. So now we are moving into the part 3, which is a continuous formulation of optimal transport and interesting things about it. And probably, I think, what is the cutest, I would say, result in the theory, or at least one of the cutest, which is this Gangbo-McCann-Brognier theorem that is going to link a lot of what we've just presented, couplings and potentials, with the goal of computing a Morse theorem. So let me, again, take a step back and recall a big motivation for some of this work. In single-cell genomics, what you do is that you take some tissue or biopsy of a patient. You're given thousands and thousands of cells. And what you're going to, what we are able now to do, because we want to somewhat personalize treatments to patients, is to take a bunch of those cells, split them open, and look at RNA, messenger RNA in those cells. And this tells us at any point in time, at that point in time, how much of each of the genes is expressed in that particular cell. So it's a bit like a radiography of the activity, of a cell at that point in time. And we are going to essentially turn those cells into points into the dimension of how many genes we are looking for. So typically it's a few 30,000. And what we want to somewhat understand is what is the effect at the level of each cell of a cancer drug. So you give the drug to remaining cells. The cells grow, they die, they multiply. And then we are going to take another sample after we have given this sample of cells in the drug, the treatment, and we're going to get another sample of cells. So this is a few thousands of cells again. And so we have a population of cells, a sample of cells before treatment and after treatment. And again, I want to emphasize that ideally, what we would love to is to be able to look at a cell before treatment, give it the treatment, and look at the cell after treatment. Unfortunately, this is not possible because most of the methods to do these measurements are destructive. So the only thing we can hope for now is just to have access to population level data. Cells before, cells after treatment, and we don't know, we can't match them. So here, the idea of optimal transport is going to be to try to infer from those two samples a notion of mapping that tells me if I have a cell somewhere, where would I expect it? What would I be expected to become in this space of genes after the treatment? So this is a bit where we're trying to fill in here with optimal transport the lack of knowledge of how to match those cells. Here, what we are going to do is look not so much for an assignment, which is going to be this discrete object that depends on the data, but more like a mapping, a function. And so people call those mappings Monge maps because of, this is Monge's name. So because Monge wrote a theory for optimal transport actually much earlier than everyone else. This was 1781. And he attacked directly. If you look at the drawings, everything is continuous. It doesn't use the same grammar that we use now for probability distributions. But if you look at the paper is already continuous in a continuous setting. And Monge asked the following question. He said, imagine I want to map this red measure onto this blue measure. So in Monge's words, the red measure was a measure of dirt or earth, and the blue measure was a hole. And so he wanted to fill up a hole that had the same volume as piles of sand and find the most efficient way for a worker to do this. So for a worker to do this, what the worker had to do is go to every point X where there was some sand and be told where to land the mass at T of X. So we're going to parameterize, we're going to switch completely gears. Rather than looking at permutation matrices or coupling matrices that are discrete, that really depend on points Xi's and Yj's, we're only going to look at two densities, and we're going to formulate everything in terms, we're going to contain all of our instructions in a function that takes, I'm going to simplify, I'm going to assume everything here is a vector, that takes a vector in and a vector out. And so if I need to specify this function T, if I can do this, I will actually tell the worker, I will give the full set of instructions to the worker. What I need to do, though, and that's hard, is to make sure that this function T does the job. It actually manages to push all of the mass in the source measure to the target measure. And so this is usually written as T push forward mu is equal to nu. So the image measure of mu with the action of T is equal to nu. And what this entails is the following. It says, if you just take any set, any measurable set in the support of the measure nu, I'm going to take this one. If I keep track of where the mass, according to my map T, landed in B, so I'm going to call this set here, basically it's the image, the inverse in terms of sets of B, which is all of the points X in the original measure that send mass to this target set B, then I need that the measure, as quantified by the measure of mu on B here, is equal to the measure of mu on this inverse image set T-1 of P. And if this is true for every set, this is a mathematical way to just quantify what we see intuitively, which is that essentially, if I were to apply T to every part of the measure mu, I will recover the measure mu, okay? And if you think about this, if you replace in your mind mu and nu by two discrete measures of size n, essentially mapping T here is going to be the permutation. But here, this is more generalized because we have the notion of mass and density. So this is what people call a Monge map. Sorry, this is not even a Monge map yet. This is what people call a push-forward map that actually pushes mu to nu. And it's actually quite hard to think about this constraint. It's not an easy constraint. In particular, this constraint that T pushes forward mu to nu is not convex. If I have two maps that do the job, if I average them, I'm not necessarily going to get a map that does the job. So it's actually quite a tricky constraint. And what Monge asks is not only that, I just want to push forward, but of all the maps that push forward mu to nu, give me that which on average incurs the least displacement cost. So what is the displacement cost? It's going to be, well, what is the cost, because I still have this notion of cost, to go from x to T of x. Now I'm going to sum up all the costs that are going to be weighted by the source measure. And this is going to be my transport cost. And now of all the maps T that do the job of going from mu to nu, give me dt that has the lowest cost. But as you can see, it's a very ambitious program. And we will see that there are ways to actually recover this map quite elegantly. So to do this, we will need to, again, switch gears in what we've seen so far. So what we've seen so far, remember, is coupling matrices, some masses which are pointwise. We need to have mass conservation, so the matrix row, column sum. Then we also saw the dual A price for each xi, A price for each yj, this constraint, and this kind of integration, the dot product between alpha and the weights, beta and the weights. What we're going to do is generalize, as you can probably expect, it's kind of a very natural generalization, the idea of now considering joint coupling densities. Those are going to be densities on the product of the two spaces with marginals mu and nu. Our double sum, Pij, cos of xi, yj is going to be a double integral, as you can expect. For the dual problem, we're going to have the same thing. We're going to integrate, instead of having alpha I, beta j's, we're going to have two functions, phi and psi, which can be integrated against mu and nu. Our alpha transpose A plus beta transpose B is just those two integrals. And the constraint that was before alpha I plus beta j smaller than the cos of xi, yj is now going to be this everywhere applicable inequality. So those three things now form this continuous basis of optimal transport. And in general, in many papers, you will rather see those definitions than the discrete ones. Now, if you want to visualize a bit what is the space of joint couplings, it's quite easy. In this case, I've just taken that the base space is just R. Those are two 1D distributions. And this is a valid coupling. It's basically a surface plot in this case, where I'm going to have a density for all pairs xy's. And it's very easy to come up with couplings. You can take the product of the measures, but also this is another valid coupling, for instance. So now that we have defined those two continuous formulations, let me take a step back. The game now will be to somewhat use some of the stuff that we already know about this primary and dual problems. We've formed quite solid intuitions about this, even though we did this in the discrete case. But this is going to be all continuous, but it's roughly the same ideas. We will try to link those two problems, the Kantorovich and Kantorovich dual problems, to this, like the Mount Everest in a way of optimal transport, because it's hard to compute this Monge map, and try to see if we can actually link the three together. So to do this, we will be using some tools that are very specific to optimal transport theory and which are quite interesting and quite fun. So let me bear with me for a few minutes, maybe 15 minutes, 20 minutes. We're going to do a bit of math, and I will try to make this as intuitive as possible. So the first step is we're going to look at the dual formulation, because the dual usually is a bit lighter. It's a bit simpler to think about functions that integrates against mu and nu rather than coupling. So the first game here is to say, okay, I have my soup of two functions. So by the way, this notation is phi x plus psi y. It's like a tensor sum of functions. So this function phi plus psi is a function of x and y, and it's equal to phi of x plus psi of y, and this needs to be smaller than the cost function c of xy. So let's play a game. I give you a red function, okay, the function that corresponds to the prices or the potential for the first measure. And I ask you, what could be a good blue function? Okay, what could be a good second potential? The original problem basically runs both variables, right? It tries to optimize on two variables, but let's just, for a second, think about just fixing the red function and trying to find a good blue function. So what do we know about the blue function? Ideally, this has to be large. This is a non-negative measure. This is a psi. So as far as I'm concerned, the largest psi is, the happier I am. The only problem that I have is that psi needs to satisfy this constraint. And this constraint, remember, is that phi of x plus psi of y needs to always be smaller than the cost between x and y. In other words, psi of y, I'm still looking for a blue function, must satisfy this. So for every y, I have a bunch of values, cxy minus phi of x, where x is whatever, that I need to be smaller to. So if my psi of y needs to be smaller to a lot of values, it's equivalent to saying that my psi of y needs to be smaller to the infimum, to the smallest of all those values. If this is true, then I satisfy this for every x. Okay. So to recap, psi needs to be as large as possible because that makes my soup happy, but it needs to satisfy at every point y the fact that it's smaller than this. Okay, so if that's the only thing that I need to satisfy, I might as well say that my phi blue transform, or the best blue function given a red function phi, is actually directly equal to this inf of cxy minus phi of x, okay? So if I recap, every time you give me a red function, I can come up with the best second potential or blue function that matches it. And this is the definition that I came up with. It's, you give me a red function, you do this inf of x of c of xy minus phi of x, and this turns into a function, a blue function. So if this if this rings a bell to some of you with respect to something like Legendre transforms or convex conjugates, it is very much similar, except that this generalizes the Legendre transform to an arbitrary cost. If you actually replace the cost here by the squared Euclidean distance, you can find some correspondence between this blue transform here that I'm showing and the Legendre convex conjugate. Now, since I'm now able to deterministically, set a blue function that is the best for the red function, I can simplify my optimization problem and say, actually, I'm sorry, I'm switching a bit notations here and there. Please bear with me. This is still the same notation. This is still Wasserstein here. But I can say, for instance, that this thing here now is a bit simpler, at least conceptually, because it's a supermum over all red functions of the integral of phi against mu, plus now this weird blue transform. So this looks simpler because at least there's no constraint anymore in this part. The problem is I've transferred most of the difficulty of the problem in this blue transform, because computing this blue transform on paper requires solving every time I'm evaluating this optimization problem. So it's a bit complicated, but it's elegant. But let's continue with this road. I gave you this blue transform, but you can very easily conceptually imagine that you can also do a red transform. I'm going to flip things, and I'm going to now, if the blue transform of a red function was to take an infimum with respect to x, a red transform of a blue function is going to be an infimum with respect to the other variable y minus psi of y. So if I'm only getting better by doing transforms in this way, why don't we play a game of, okay, I start with a red function. This is my variable. I apply the blue transform to phi to get the second blue function. And then I apply a red transform to this blue function here to get back a red function. And it seems to be at least improving all the time. I mean, there's no reason why it would decrease my performance. So you feel like, okay, maybe I found a secret algorithm to do this transform many, many, many times. So I start with any red function, and every time I'm going to improve. Unfortunately, you can easily prove that when you do twice, 3 times this transform, you go back to just one transform. And this also should remind you, if you know about convex conjugates, that when you take the Legendre transform many times, basically you are doing it's idempotent. After a while, you're not really changing anything. Still, what we have now is something that looks cool, which is the fact that we could start from any function. We transform it once, twice. Okay, 3 times doesn't help, but at least once and twice already helped us. And so what we're going to look at more specifically is functions phi that are themselves already the transforms of a blue function. And we will call those functions C-concave functions. And again, this is related to the Legendre transform. You know that when you take the Legendre transform of a function, it's always convex. So here is a generalization. It's going to be a C-concavity. So a C-concave red function is a function that is itself the red transform of a blue function. And what you can show very easily, again, if a function is, if you apply the Legendre transform twice to a function, you get back the same function, then this means that the function was convex to start with. And so we are going to basically have this identity here. So the game here, I know it's a bit tedious, this blue and red transforms, but it's a game where we started from a very general, optimization problem with 2 function variables. And what we got to now is saying, well, if I can characterize functions that are C-concave, I can only focus on those functions because they are actually probably giving me the best solution anyway. And I can also look at this problem here, and what if you could say something about the blue transform of a C-concave function? So there's one very specific case where actually this is very simple and very nice. And it's the case where the cost is a distance. So this was the problem that was considered by Monge originally. So if the cost is a distance, what you can show is the following. If a function is deconcave, or let's say a function is deconcave, if and only if, its blue transform is equal to minus itself, and phi is 1 Lipschitz. So I will not prove because it's in the slide, so if you want to download it, but the proof is not too complicated. It's a few lines, so it will take me 3-4 minutes to explain it. But you can actually show this. So what we did is we showed that, with this game of C-concavity, we were basically playing with, we can only focus in this dual problem on a specific subclass of functions which are C-concave. It would be great if not only I knew what a C-concave function is, and it would be great if I knew what the blue transform of a C-concave function is. That would be nice. And it turns out you can actually say something very clever about them when the cost is a distance. When a cost is a distance, a function is deconcave is equivalent to saying that its blue transform is minus phi, and phi is 1 Lipschitz. So what we have is a very nice characterization of what people call the Wasserstein 1 distance. The Wasserstein 1 distance is a supremum over all 1 Lipschitz functions of the integral of phi against mi minus nu. Of phi against mu minus nu. And as a parenthesis, and I'm guessing Arthur might be talking about this later in his presentation, in this case, and in this case only, the Wasserstein distance is what people call an integral probability metric. It's basically trying to figure out how far mu and nu are by trying to find a test function that discriminates them maximally. Is able, to split them maximally. But of course, you need to put a constraint on phi for this to make sense. So here we're using 1 Lipschitz class of functions. But that's it. Now I give you the best result in optimal transport theory, in my opinion, which doesn't apply to the previous case, unfortunately. The result is the following. We have played with the blue transform, remember? We said, if I give you a red potential function, I can give a blue potential function. we have talked about the fact that the optimal solution must be C-concave. So we can always find the best potential is C-concave. And the result of optimal transport theory that is actually beautiful is to say the following. If you work hard on this dual optimization problem and you find a potential phi star that is optimal, so it doesn't sound completely far-fetched. It's actually, even I will show later that you can find finite sample estimates quite easily for that potential. Then the result that Gambo and McCann generalizing a theorem by Brognier proved is that the optimal transport map, the Monge map, is a map which to X is going to associate X to this ugly or beautiful formula, which is as follows. It is the map. So here we have this composition of two maps. So here, this part is easy. It's the gradient of phi star. So again, phi star is the potential, remember, so it goes from RP to R. The gradient of phi star is going to be something that associates a vector to a vector. So here we are expecting to see a vector on the left-hand side. So it's actually good that we have a vector on the right-hand side as well. But we are going to apply a map to that vector here on the right-hand side. And this map is this so-called twist operator, which is going to be the following thing. It's something, which to a vector associates the gradient with respect to the first variable of the cost. And this is going to be computed at X. And it's going to be the inverse map of that operator. Okay, so let's forget for a second about this -1 because maybe it's a bit easier. This thing here, my notation here means the mapping with a fixed X, which to a vector Y associates the gradient with respect to the first variable of the cost computed at XY. So this takes a vector in and outputs a vector out. And I'm just using the inverse mapping of that. And I'm assuming the inverse is well-defined and is basically injective. Okay, so this mapping is injective. So maybe if I show you the proof, you will get a better intuition for this. So the proof goes back to the following, primal dual relationship, which I had stated, you remember, in the discrete case. In the discrete case, I told you if we have a matrix that is a coupling matrix and we have two dual vectors of prices, then the fact that some mass ij is transferred, so the entry at ij of the coupling is positive, is equivalent to the fact that the prices of alpha I plus beta j is equal to the cost to go from xi to yj. Here it's going to be the same. The primal dual relationship is going to be exactly the same. If there are 2 points x0 and y0 where the coupling has mass, so x0, y0 is in the support of this optimal coupling, this is equivalent, this linear programming duality, even if it's continuous, to the fact that the two potentials, phi star of x0 plus psi star of y0 is equal to c of x0, y0. So that's our starting point. I'm going to pick 2 points, x0 and y0, where there is some mass. Now, if I have this relationship, you remember that I told you several times that actually this psi star here is a bit of a dummy variable, because I know that I can change this psi star into the blue transform of my red function. Okay, I cannot do better than by doing this trick, so I might assume as well that this is the case. So this means that if x0, y0 is in the support, then I have this relationship. This means in particular that I can just flip here this term here and put it on the right-hand side. And so I have this identity. Okay, whenever x0, y0, whenever there is mass at x0 that is transferred to mass at y0, then this equality holds. Now remember one thing. By definition of this blue transform, I told you that actually this blue transform is doing a great job of taking the infimum over all z's or x's of the cost between z and y0 minus phi star of z. This was by definition, something that I wrote here. Okay, so I have two facts which are given to me. One is because x0, y0 is in the support of the coupling, I have this equality. But also by definition, this thing here holds. So if you look at those two things, I'm telling you, x0, phi star of y0 is equal to cx0, y0 minus phi star of x0. Okay, that's what I got from these KKT conditions. At the same time, I have this. So this means in particular that if this equality is valid, x0 must be a minimizer of this energy, okay? And this is an unconstrained optimization problem. So if it's the minimizer of this energy, this means that the gradient with respect to the first variable of the cost at x0, y0, minus the gradient of phi star at x0, in other words, is equal to 0. In other words, I have this identity, okay? I must have this identity for this to be true. And now is the inverse part. Now, if I tell you that two vectors are equal, then one vector depends on y0. If I'm able to inverse this operator, which to y0 associates this gradient, then I can write that y0 is equal to something. In other words, what I just told you is I started from the idea that, okay, let's imagine I run all of my optimal transport computations. I have an optimal coupling. There's mass that goes from x0 to y0, blah, 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 blah. Actually, it turns out that there can only be one y0 if this operator is invariable. There can only be one y0 to which you associate mass. And therefore, I started from x0. I landed mass on just one y0. That's the only one that works. And it's equal to this. So therefore, I have a map. I have something that associated one x0 to one unique y0. And this is my optimal transport, my motion. So this is a bit this Gangbo-Macan theorem. What is beautiful is that it essentially relies on whether this cost function has this twist property. It is this mapping is invertible. And if this is true, then by running the dual optimal transport problem, getting this potential function phi star, I'm done. I can give you directly the mode map without ever optimizing this very nasty push forward constraint. So let me give you a few examples where actually this is a bit more interpretable and easier to handle. Let's assume that the cost is a translation invariant cost. So the translation invariant cost is just simply saying that it's the cost between x and y is equal to some function h of the difference. So you all know h being the squared Euclidean distance is going to be just the norm, right? So it's going to be the squared, h being the norm, the Euclidean norm is giving you the distance. So I am going to assume that h is a convex function. So it is something that goes from, I'm sorry, it's maybe a p here. I'm switching between d and p a bit randomly, but this is basically your base space to R. So if that is basically my definition, things simplify a lot. In particular, if you take the gradient with respect to the first variable x of the cost, it's the same thing as taking the gradient with respect to h, the gradient of h, sorry, of the difference x minus y. This is a very simple identity. So if I look at my operator here, my pre-twist operator, before the inverse, essentially this operator is something which to a vector associates this gradient is the same thing as saying that it is the operator which to a point associates the gradient of h grounded at x, minus this point. And the inverse, it's a very simple identity. It's going to be equal to x. So again, x here is a fixed point. It's the point that I'm starting from, so I know it. It's going to be, this operator is going to be the operator which to a point associates x minus the inverse map of the gradient associated to this point. Now, if you know a bit about convex duality, convex conjugates, what we know, this is a very important result, is that if h is strictly convex, the gradient of h is an invertible map. Gradient of h is something which maps a vector to a vector. It turns out that the inverse mapping is equal to the gradient of the Legendre transform or the convex conjugate of h. So if you give me any convex h that is strictly convex, usually I might be able to come up with its Legendre transform or convex conjugate. So if it's the square Euclidean distance, but it's itself, it's basically it's the gradient of h is the identity and the gradient of h star is the identity as well. So if I know h, and I'm free to define it, this is the cost after all, then I can essentially, come up with a much simpler formula for this fairly complex twist operator. It's something to a point which associates x minus grade h star of the point. And again, for those of you who are not familiar with convex conjugates, This is the definition. And I'm asking you to just be mindful here, be careful that this star is not the same thing as this star here. This is the optimality star, and this is the convex conjugacy star. So I'm going to keep on, my simplification, dumbing down a bit this beautiful theorem. If I have a general cost function and this operator is invertible, this is the optimal transform map. And this is going to be a phi star that is computed, with this general cost function. I don't want you to think that those 3 phi stars are the same, right? That each phi star is the best potential for the specific cost it is defined with. For translation invariant cost, the more, this Gangbo-Macan-Brognier theorem tells you this. And now let's dumb things down a bit more. I am going to use just a squared Euclidean distance. We're all familiar with this. For the squared Euclidean distance, my definition is that h is 1/2 of the squared norm of a vector. And so I'm applying the squared norm to x minus y. Remember, this is translation invariant cost. So it's a cost of h of x minus y. In that case, the gradient of h is the identity. And it's also the gradient of h star, the convex conjugate of the parabola is the parabola itself. So everything works. So everything is identity. So this means I can remove this thing. And so this is known as the Brognier theorem. The Brognier theorem tells you that the optimal transport is x minus grad phi star of x. So there's one thing more that I can say about this very last case that is very interesting. Remember when I was using the distance in the Wasserstein one setting, I told you that the blue transform, sorry, a function that was distance concave was a function that was Lipschitz, one Lipschitz, and such that the blue transform was minus itself. Well, it turns out, I'm not going to prove it, it takes a few slides, that if I look at this equality here, I can also rewrite it if I'm a bit fancy by saying that here this is the identity of x minus grad of phi star. This is the same thing as taking the gradient of the square norm. Again, the gradient of square norm is identity, minus phi star applied to x. And you can show that this thing here is convex if phi star is C concave. So it's a bit of a technical lemma. But what essentially you can show is that T star of x is equal to something which is the gradient of a convex potential. And that convex potential is 1/2 of the parabola, basically, minus phi star, the usual dual potential. So you can rewrite or rename this parabola minus phi star. You can call it basically F star. And it turns out that F star looks a bit like the phi star, but it's solving a slightly different problem. It is basically solving the problem of finding a convex function that minimizes something like this. So this is very similar again to the dual problem. Remember, the dual problem was a soup of F that was C concave, and there was F plus the blue transform of F. Well, it turns out that if you use the square Euclidean distance, you can evacuate some of the quadratic terms and you flip some signs, etc. So this is also known as the Brognier theorem. The Brognier theorem is telling you the optimal transport is a gradient of some function that is convex. The function can be recovered by minimizing this problem. This problem is nice, but there is a Legendre transform in there, which is a bit complicated. It's a bit nasty, but maybe we can handle it. So this is again, the cornerstone of a lot of results in optimal transport theory that are out there. And I would say this is very exploited by now. People have started to play with this, and people don't really touch a lot this for now. So let's go back to our original motivation to compute Monge maps and try to use these tools to come up with functions that do transport between those samples. So one of the approaches that was proposed is to do this because a lot of the computations that we're going to do are a bit cursed by dimensionality. A proposal was to lower the dimensionality of those points. So you could use PCA or you could use VAEs, like a pre-processing step. And we're going to be a bit more comfortable doing this transport in a lower dimensional subspace. If you have an autoencoder, you can then decode to go back to the original space. If you're using PCA, you can just reinflate after prediction if you really want to predict in the gene space. So what we have tried to do in multiple occasions was to come up with a mapping, again, that is going to be the squared Euclidean distance in your optimal transport map, the Monge map for this squared Euclidean cost. And if you followed what I told you, you know that by definition now, if all things work out properly, the T star that we have for a given drug should be equal to the gradient of a convex potential, F star. And F star, again, is going to be an infimum over convex functions of this integral. Now, what we are going to do, because we love neural networks, is come up with a family of neural networks that are convex with respect to X. So this is called input convex neural network. This was proposed by Amos a few years ago, Brandon Amos. And we are going to try to minimize this energy, which is not so simple, because this part is very simple. You know, it's just the integral of f theta of x. But this one is using the convex conjugate of a neural network, and that's something we can't really compute in closed form. So we're going to come up with a few workarounds. But let me explain for a few seconds what I mean by a input convex neural network. So an input convex neural network is just going to be a neural network that guarantees. So it's a neural network that will take an input vector and output a value. And I would guarantee by construction that this function is convex. How can you do this? There's many, many ways. But that which was proposed first by Brandon is basically to start with a vector. This is going to be like a state vector of arbitrary dimension. I'm going to set it to 0. And I am going to make some update, where at each layer, I am going to update the state vector here with a function element-wise of a vector. And the vector is going to be a combination of the previous state vector, a combination of the inputs, and some bias vector. So let me just try to plot this here. I will start with a state vector that is maybe zeros, could be more complicated. I have my input x. I am going to inject into the state vector affine functions of x. So each entry of this, this is going to be a vector here. Each entry of this vector is just a linear function of x, and the linear function or affine function is a convex function. And I'm going to mix the previous entries of Z0. So maybe if Z0 was zeros anyways, maybe nothing is really happening here. And I'm going to use an activation function element-wise, on this vector. And I'm going to do this repeatedly, like this. And I am going to combine at every layer the previous state function with a refreshed affine transformation of x. And at the very last layer, I'm going to collapse everything to one single number. So by making sure that the last basically operator is just the transpose of a vector, and here the same thing for x. And again, a nonlinearity, and then a value that is just a real number here. Well, if you do that, and if you use non-negative mixing weights for the state vectors, then, and also you state that all of those activation functions are increasing and convex. So like soft plus or ReLU or anything that is basically like this, or even a linear function if you wanted, then f theta of x is convex. You can guarantee this. So we have two things that we need to keep a track of is we need to have non-negativity of the mixing weights for the state vector only and increasing convex functions. So if you have that, you can guarantee that this is a convex function. You can come up with more advanced, more sophisticated ICNNs. Nina, who might be in the room, presented a poster last week where she was using quadratic activations. So this is the neural network parameterization part. We're happy we have a neural network that is guaranteed to be convex. So our plan, remember, was to take the infimum over neural networks that are convex of these two terms. And here this term is nasty because it's the convex conjugate. So it's an implicitly defined, function. It's not explicit. So what a bunch of people, Makuva and others have done is that they have proposed to actually replace this f theta star by a surrogate function that should look like the convex conjugate of f theta. And in order for this look like, thing to have a quantification, you can use this kind of penalization. I'm not going to go into the details, but essentially this quantity here should go to 0 if omega is indeed the Legendre transform of F tilde. So there's a few challenges with this, I would say, and they have also been quite investigated. And we have a tutorial on the OptimalTransport page that also shows basically how this can be done using some of the tricks that were proposed by Brandon in a recent iClear paper. So this actually, I'm going to be brief on this. This actually seems to be working very well in some genomics, single-cell genomics tasks. This was shown by Charlotte in a recent Nature Methods paper. But I'm going to be brief. I'm also going to be brief on a NeurIPS paper that we had 2 years ago that tries to actually, rather than for each treatment, learn a new Monge map. It is going to learn some kind of hyper network that is able to produce a new map depending on some drug feature vector. But I'm going to be brief on this because it's a bit complicated and I'm going to run out of time. But then I'm going to also show another approach that is also neural-based, but that is a bit more flexible than this input convex neural network. So what I showed you, is that we have this fantastic result by Brenier. If the cost H is a squared Euclidean norm, what I just told you is that we can parameterize the transport map T as the gradient of a convex function. And therefore, let's just focus on neural networks that are gradients of convex convex functions, basically. Or sorry, let me retake that. Let's just focus on gradient on functions, neural networks that are convex, and take their gradient to parameterize transport. And we've shown that we can use some kind of dual formulation for this to optimize the weights of those neural networks. What we propose in a recent paper with Teo Ushida is to lift a bit this restriction that we only can parameterize transport maps as gradients of convex neural networks by just instead turning this idea of an optimal transport map as a regularizer. So essentially, if you want to parameterize transporting from points to a point cloud to another point cloud, if you really follow this optimal transport dogma and you're using the squared Euclidean distance, you might want to parameterize your transport as a gradient of convex function. What we find more useful and a bit more flexible is that just use any MLP or neural network that takes a vector in and outputs a vector. And rather than constraining it to be gradient of convex function, penalize any transport that does not look like an optimal transport. And so the question is now, how can we come up with a regularization that penalizes functions that do not look like transport maps? Well, it turns out we can come up with something called the Monge gap, or some kind of gap to optimality, which is going to be this definition. The gap to optimality, or so the penalization that tells me whether a map F is or not, does look or doesn't look like an optimal transport, is going to be the following thing. It's going to be just the cost of moving mass from X to F of X, according to some reference measure, minus the Wasserstein distance between this base measure pushed forwarded by F. So the formula may not be too intuitive, but let me just show you this drawing. Imagine I have a sample. Okay, this is X1 to X4. And I am giving you a map. And the map takes vector in, vector out. And this is the map. Okay, so the map basically took, I'm sorry, the arrows here have been spuriously added when I converted the slides. So please disregard those two arrows here. Here I took X1, X2, X3, X4. My map F pushed basically those points to Fx1, Fx2, Fx3, and Fx4. So if you look at this map, you intuitively know immediately that this doesn't look like an optimal transport map, right? It doesn't seem to be moving things very carefully or optimally. Why do you think that? Well, because if you run an optimal transport problem on the base measure that I just gave you and the output of F, you can do the job, can compute internally a better way of moving from the X's to the F's. So this tells me in a way that f, whatever it's doing, it landed the point somewhere, but it didn't do this in a clever way, in a way. I can always find a better way to start from where f started and land where f landed, okay? And so what we're going to do is we're going to quantify the difference between how well, this optimal transport map T is doing versus f. And the difference, if you're just using the distance, is basically these two segments A and B. So what we call the Monge gap in this case is simply the sum of the lengths, of this red and these two red segments here. But the important thing to consider here is that my regularization here seems to have involved the optimal transport. But here I just use the optimal transport for illustration. The optimal transport cost, basically the sum of the yellow lines, is just simply equal to the Wasserstein distance between this set and this set. So whenever you give me a new function f that takes vector in, vector out, I just sample a few points. I just look at what this function is doing on those points. And now I'm going to compare the cost of displacement from x to f of x, all of the sums of those segments, minus the Wasserstein distance between those points and those points, without knowing basically what their matching is or where basically which point went where. And so once I've done that, this is a quantity that is non-negative. Because if f is optimal with respect to this cost, then this will always be 0 by definition. And if it's positive, it means that f is not doing as well as what could the best possible map do. So this is a nice regularization that basically tells me how optimal my f looks like. And so when you look at this for the squared Euclidean cost, you can say a few properties about it. And in terms of computations, again, the entire challenge here is just to have access to a quick estimate of the length of the optimal transport, basically, or the Wasserstein distance. And this we use entropic regularization. So we use a subroutine, which is going to use Synchron in a way. And we can differentiate that Wasserstein distance again using Danskin, as I said earlier. So I'm going to be a bit quick, but one of the nice things about this regularization is that it allows you to even envision optimal transport maps that are optimal, for a cost that is not necessarily square Euclidean distance. You don't need this input convection network anymore. So this idea of this Monge gap. We also have a tutorial on this in the toolbox. Now, a more recent line of work is doing away with neural networks. And we are going to try to come up with estimates that are actually going to work using the outputs of Synchron. So it's going to be finite sample-based estimates, and they will look a bit like regression or nearest neighbor type estimates. So I'm going to be a bit brief about this. If you're interested, we also have a tutorial on this. So the way you can actually get an estimation of T star, remember, is by having an estimate of the best. So I switch here notations. I'm using an F instead of a phi. I usually use a phi for this. But if you bear with this slight notation change, the goal was to come up with an optimal dual potential and then inject or plug in this dual potential into this Brognier formula to get an estimate of the Monge map. Well, it turns out actually that Synchron is very convenient, but because it provides us quite easily with an estimator that is also valid out of sample of the dual potential. So what is this estimator? It's called the entropic dual potential. And it goes as follows. First, you just have points from your base measure, x1, xn, y1, ym. You run your Synchron algorithm. Remember, the Synchron algorithm gives you alpha i's and beta j's. I'm going to rename alpha I and beta j's as fi and gj's. So why am I changing this name? Because they look like some kind of pointwise estimate of my potential functions. And it turns out that this function here, I don't have time to explain exactly why. For using the same regularization for Synchron that you use in the algorithm, you can plug in the output of Synchron to define something that looks like some kind of log sum x or log of a sum of a kernel expansion. And this dual potential estimator is this minus gamma log of sum of exponential minus x minus yj. So essentially what it does is for every new red point that you give me, I am going to compare it to all of the previous blue points that I had, and I'm going to use this kind of temperature, which is this dual potential that was written by Sinkhorn. And I'm going to sum all of those exponential minus the cost plus GJs. And so this was proposed by Aram, Alexandre Pouladian, and Jonathan Niceweed for the square Euclidean distance about 2 years ago. And we extended it for any cost translation invariant cost. So with this, now the game is going to be to plug this thing here in this formula, okay? I replace my F star by my F hat n. So if you do that, the funny thing is that because my F hat n was a log sum x, you all know that the gradient of a log sum x is called a softmax. And it is basically boils down to this sum of a weighted sum, a convex combination of the gradients of h of x minus yj's. So here my x should be red if I were consistent. So please consider this is a red x here. And this red x is just a weight. It's just like, again, it's softmax, so it's going to be a weight. So it's convex combination of vectors of grad h. And the funnier, interesting thing is that if you look at what I'm doing to this grad of f hat n, I am going to plug in grad of h star, here star being the convex conjugate. And if you do that, it's very much related to something called the Bregman barycenter of a set of points. So you can see that this thing is a sum of gradients of h. I'm applying grad h star behind it. This is not something new. This was considered in Bregman geometry, and it's called the Bregman barycenter. This means that this vector here is a Bregman barycenter with respect to this Bregman divergence generated by h. The last bit of interesting thing is that if you use for h a squared norm plus any function tau, what we figured out is that essentially grad h star is equal to the proximal operator of tau. So this means that we are going to, this thing here is basically applying a proximal operator if you're using a cost, which we call of elastic type. And the proof is very trivial. So essentially what we have is that we are able to come up with transport maps using those f hat n, which have some kind of structure that you can dictate by specifying a regularizer tau that has an interesting proximal operator. So here I'm using a elastic type cost, which is the square Euclidean distance plus something called the k overlap norm. And as the weight in front of the k overlap norm increases, my estimator of the transport is basically promoting very sparse vectors. So I can start playing a bit. So this is the first step, I would say. We started with h, that was the square Euclidean distance. This was basically input convex neural networks or anything that is a convex potential. And we're moving away from this and we're having more fun with costs, which are now more structured. So I will go a bit quickly on this. Again, you can play with this in OutJax in a few lines of code. All of the plots are basically literally just using this type of thing. You can redefine costs of elastic type in OutJax very easily. So you end up having kind of sparse displacement estimators. And so anyway, so this is a bit of perspective. I will try to run into the last part this is just a few slides. So this is going to be the more dynamic formulation of optimal transport and links to flow matching. And first, a link to a Monge-Ampère equation, which is one of the big things in PDEs. So what is the link between optimal transport and PDEs? Well, it turns out that there's one very important link that is given by Bregnier's theorem. The fact that the transport is the gradient of a convex potential. So if the cost is a square Euclidean distance, remember, Bregnier's theorem says that the optimal transport between two measures is going to be the gradient of a convex potential, okay? It's grad of f star. Now, if I assume that the measures have densities, so mu is equal to p times the Lebesgue, the Lebesgue measure, mu is equal to q, okay? So this is density. Then stating that the push forward of t on mu is equal to nu is just a change of variable formula. And the change of variable formula is basically going to be that p of x is equal q of t of x, determinant of g t of x. This is just change of variable. Now, the interesting part is what happens if I run, if I am doing optimal transport. I know that t is the gradient of a convex potential. Therefore, stating that this holds for a certain convex potential is the same thing as replacing T by here the gradient of F. And the Jacobian of T here is just going to be the Hessian of F. So if I just replace T by gradient and Jacobian of T by Hessian, and I know that the Hessian is going to be actually non-negative by the determinant, sorry, I know that it's going to be positive if it's a convex potential, then this change of variable formula is equivalent to this identity here. Here I'm just basically putting P of X, putting it here below, Q of the gradient of F of X, and finding a convex potential that solves this is actually the Monge-Ampère equation. It's the Monge-Ampère PDE problem. And this is what gave a lot of fame to Caffarelli and Figali. And what they have been studying repeatedly is basically the regularity of such convex potentials. By regularity, I mean essentially the Lipschitz constant of grad F. If X and Y are in the support of the base measure, our gradient F of X is gradient F of X very far from gradient F of Y. So this Lipschitz regularity of the optimal transport map is of interest to this study. Second, there is a different type of, I'm sorry, I'm looking at, yes. There is a different formulation for optimal transport that was proposed by Benamou and Brenier in 2000, which is as follows. What they said is instead of actually parameterizing transport as one step, map that takes input measure to target measure, what we will try to do is to parameterize the entire displacement, the measured displacement, mu t basically, that goes from mu0, which is equal to mu1, which here we're going to set to nu. And if you parameterize the problem of transporting optimally, those two, having a transport that is optimal between those two measures, you are going to do two things. You are going to look for all of the intermediate measures between t, between 0 and 1. And you're going to parameterize the velocity field that is going to be time varying, which is going to have, which is going to essentially tell you at any point in time, in any part of the measure mu t, where it's going to be moved towards. It's essentially parameterizing the optimal transport in terms of derivatives, time derivatives of this transport. And so there's going to be two important variables in this dynamic formulation of optimal transport. The first one is going to be all of the intermediate measures mu t, and the other one is going to be the vector field vt, time-dependent vector field vt. And those two things need to follow the following constraints. The first thing is that we need that there is a basically continuity equation. If you look at the time derivative at any point of mu t, it has to be such that it is equal to minus the divergence operator applied to vt mu t. So this is basically quantifying how much mass is going away from basically that particular point in time. And so the mass that goes away must be equal to minus the derivative of the mass at that point with respect to time. And the two other constraints is basically, I want my trajectory of measures to start at the target, the source measure mu0 and to end at the target measure mu1. Now, the thing that we will try to be minimizing is along that interpolation of measures, mu t with respect to time t here, I expect that the measures are going to move infinitesimally for each time t by this amount. This is basically how much the vector field is pushing every point x at time t, and I'm integrating against this interpolating measure mu t. And if I just take all of this together, I get this Benamou-Brenier formulation of optimal transport, which is essentially, okay, I'm going to start from mu0, I will reach to mu1, I will try to find what is the interpolating measure between them. I will also find what is the velocity field that is going to be moving this measure onto the next step between time after time. And I am going to minimize the total amount of kinetic energy that is going to be incurred by this displacement over time. And I'm going to have to satisfy those constraints. So you see that in terms of parameterization, this kind of explodes the number of parameters that you need to keep track of. We need to have a time parameterized measure. We need to have a velocity field that is defined at every time step t and at every point. And of course, a vector field is a lot more complicated than even a measure because it's a vector-to-vector mapping. So the contribution by Benhamou and Brenier back in 2000 was to actually run this problem by discretizing both in space and time. So in space, you discretize on a grid, maybe you're in R2 or R3, and you are actually going to keep track of, mu0, mu0.1, mu0.2, mu0.3, etc. And at the same time, you're going to keep track of VT, again, which is going to be a vector field at every point in time again. If they do that, what they found out is that this problem here was not convex. This was the big problem. This is it's a bit like saying that if you have x and y, the product of xy is not a convex function. But what they figured out is they figured out the reparameterization, where instead of having this variable vt, that appears here multiplied by mu t and here somewhat multiplied by mu t as well, they figured out a way to reparameterize things by stating rho t is equal to vt mu t. So this is basically the multiplication of a vector field pointwise by a density. And if you make this change of variables, well, you can see that this here can be rewritten in this way. And here we have gone from something which is like xy to something which is x divided by y. And x divided by y is the convex function of x and y. So this is a convex formulation for both x and y. So this, I'm going to be very brief on this. Not this thing. This thing was not used, but this thing here, this dynamic formulation of optimal transport, has been used recently in flow matching, in the sense that rather than parameterizing the transport as just one-step type of application map, as we were shown before, the gradient of the convex potential, etc., what people have proposed to do is parameterize transport essentially as an ODE. So the VT is what is going to give basically this progressive displacement, and integrating this ODE is going to give you from a starting point x0 a landing point x1. And what we know from also optimal transport theory is that in principle, if we are running this machinery with squared Euclidean distances, the trajectories of the particles that follow optimal transport should actually be straight lines. And so this insight was used in the first flow matching paper, which basically tried to propose, oh, sorry, I'm going to say this was built on the precedent of continuous normalizing flows. But essentially what this machinery tries to do is to sample points from the starting measure mu0, the ending measure mu1, create this interpolation between x0 and x1 at any point in time and call it xt, and essentially look at this vector field, which is given by this interpolation, and try to regress the velocity field that is used in flow matching. And so by sampling both time and by sampling both endpoint and starting point, and drawing a straight line between those points and trying to regress the vector field, what they show is that even though this sampling is naive in the sense that it only takes points from the two marginal distributions, upon convergence, at least in theory, this should converge to this optimal field VT. And of course, this is going to be parameterized by a neural network. It's going to take as input both time and x. A recent wave of works tried to do something a bit more clever. They tried to sample not one point from mu0 and one point from mu1, but rather multiple points from both measures, run a discrete optimal transport solver to get a P star, and then sample x0 and x1 a bit more conditionally, a bit more effectively, according to this optimal transport discrete-based transport matrix. So this is concluding my presentation. I'm aware I'm running a bit late. Thank you very much for your attention.